A very big hello to all my dear students. So today let's start with the chapter optics. Now before I start with this chapter, please remove all the phobia that you have inside your mind regarding the chapters optics, squint, retina. So while you're studying with me, you'll realize these are very interesting and simple chapters and definitely you're going to enjoy it. But the first thing that you have to keep in mind is leave aside all the phobia. Oh, it is a difficult chapter. It is not at all. Okay, so let's start. Give the heading Visual Perceptions. So the first thing is we are going to learn in the optics chapter is what are visual perceptions. So visual perceptions, do you all realize there are 4 visual perceptions in our eye, right? One is called the form sense. Second is your light sense. Form sense means, what is light sense? Let's start with light sense. Light sense means when you know it is day or night, the light is on or off, that is your light sense. Form sense means actual looking at the things. You're writing with a pen, you can recognize the copy, the pen. This is your form sense. That is recognizing the form. Third is your contrast sense. And fourth, write down color sense. Okay, we'll take one by one. Contrast, sharpness of image, and color sense is when you perceive the color. So we take one by one. First is your, okay, let's start with what do you mean by light sense, all of you? What did we say? That is what we document as PL and PR. What is PL? This is perception of light. This is what is called PL. Right? So this is my light sense when I can understand whether it is light or dark. Okay? Simple, right? And what is your PR is projection of rays. Projection of rays. Now, how do I check it in your eye? So if you're standing in a dark room and I'm putting a torch in your eye and asking if you can actually make out the torch, light is on or off. If a person is not able to see anything, it will be dark for him all throughout, isn't it? So perception of light is easy to understand. Now, what is projection of rays is, this is my torch, I am throwing the light from different directions, okay? So I'm asking the patient, so if you're the patient, I'm throwing the light from here, above, side, and I'm asking you from which direction I'm throwing the light, right? From where is my torch? Is the light coming from this direction or this direction or this direction or this direction? So actually it generally sees the health of the peripheral retina. Okay. So this is what is projection of rays, and we generally depict it with a cross, and we are going to mark it, whether it is positive. If everything is fine and the person can tell, I'm going to document it as positive, or in any direction if there is a defect. For example, these are examples. Then of course it will be like, okay, here there is some problem with the projection of the rays. So that was about your light sense. So can you understand the projection of rays can be affected wherever the peripheral retina is affected first. And we have learned one disease where peripheral retina is affected first, or the peripheral vision, that is glaucoma. Or it could be retinitis pigmentosa, right? And so on. So it is helpful in these diseases to understand the health of the peripheral retina, like glaucoma or retinitis pigmentosa and so on. Then we talk about what form sense. Okay, how do you see you have understood what is a form sense, right? So what is the measure of form sense? Form sense is measured by, this was your exam question, we put a Q and the language of the question was, visual acuity is a measure of which sense? And the answer was form sense. So please remember, form sense we are measuring by a visual acuity. So visual acuity is a measure of form sense. Now, when you say visual acuity is a measure of form sense, how do you check that? We check it with a Snellen's visual acuity chart. Sabse pehle, first of all, let us talk about Snellen's chart. And I think I also taught you that whatever central vision we are checking, it is through this visual acuity checking of visual, or the central visual measurement is all nothing but visual acuity measurement, right? So let's look at the Snellen's chart, and we have to study in and out about it. Okay, so this is your Snellen's acuity chart. I think everyone is familiar with this. We all have gone through eye test, or we have worked in the IOPD, so we know this chart well. I'll start from the basics, though I have mentioned in earlier chapters also. What do we mean by 6 by 6, 6 by 9, 6 by 12? So 6 is the numerator. 6 is actually the distance at which your patient is sitting. So if the patient is sitting at 6 meter distance, which is 200 feet, then 6 by 6 or 6 by 9, what does it mean? The denominator is the vision of a normal person, right? So when you are able to read the last line DNHOBUC, your vision is normal. Compared, a normal person could also do the same. But if your patient says that I can see only up to DHLEN, in that case, it simply means that this size letter could have been read by a normal person by 12 meters, but my patient is able to read it only at 6 meters. So when I say 6 by 24, again it means that a normal person can read this at 24 meters, which my patient is reading only at 6 meters. Got it, all of you? So this is the basis of documenting the visual acuity, right? Okay, so I think you have understood this, that these are the lines here, that this is your 6 by 6, 6 by 9, 12, then 18, 24, 36 and 60. Now, another very important thing is, what do you think if I just make you sit at 6 meter distance and I start writing on the board ABCD, I tell you, okay, close one eye and start reading it. Is it a correct method of taking the visual acuity measurement? Should I just make you sit at 6 meter, write some letters and ask you to read? No. Because the size of the letter on the Snellen box has got some scientific basis. Now, what is that scientific basis? So, every letter in the Snellen's box subtends, suppose I take the letter E that was written in your Snellen's acuity chart, which was a 6 by 60 letter this big. Or it could be any other. Every letter, whole letter subtends an angle of 5 minutes. Okay? Where? So, you know, angle is depicted by degree and 1 degree is 60-minute arc. So, it is lesser than the degree we are talking about. So, 5 minutes. And the margin, I'm just making a rough thing here that overall it is this. You can just draw this for your understanding. And the margin of the letter subtends an angle of 1 minute. So what I'm trying to tell you, first of all, where is this angle formed? At the nodal point of the patient's eye. Have we not talked about nodal point introduction chapter? Let me quickly revise it for you. What was the nodal point? It was the first focal point, which is considered the optical center of the eye, situated just behind the lens. So, at this nodal point, the angle subtended by every letter in the Snellen's box is same. And this is the reason the size of the letter is very crucial, and I cannot just roughly write something and ask you to read. So, but you must be thinking, how is it possible? One 6 by 6 letter is so small, DNHOBUC, and the 6 by 60 is so big E. So, I think ma'am is not teaching correctly. By every letter, how can it subtend the same angle at the nodal point of your eye? So, what is the difference? Let's go back there. So, what is the difference here if I say all the letters are subtending the same angle at the nodal point? Difference is distance. Okay. So, do you realize, have you learned in your physics also, that the size of image will depend not only on the size of object but distance of object from the lens, isn't it? So, what did I want to tell you here? That 5 minute and 1 minute subtends is same, but the distance is different, which means if I look at this letter D, this will subtend an angle of 5 minute and the margin is 1 minute from 6 meters, whereas an E here is subtending the same angle from 60 meters. So, keep this in mind. Correct? Okay. And it is always, the margin is what is called minimum and the margin, that the angle subtended by the margin, this is your minimum angle of resolution. We will also call it minimum angle of resolution. MAR is, write down please, it is minimum angle of resolution. Okay? Okay. If we know this and we have understood this, so what do we want to say here? I am again repeating it so that it should be absolutely clear with you, that uppermost line is subtending the same angle of 5 minutes and 1 minute at the nodal point of the patient's eye from 60 meter distance, whereas the last line is from 6 meters and so on, 9, 12 and so on. I think it's correct now? It's clear? Okay. So you will realize that overall whatever the angle is subtended by the letter is always 5 times that of the minimum angle of resolution. Now we have to understand why. A quick revision of what we just said is this. So can you understand here? It is the distance which is different, but the angle subtended becomes the same. So it is the same letter E when it is small, at 6 meters is subtending the same angle. This is a different distance, this is at 60 meters. It is the distance which is differing. Now, why it is always the 5 times? So a Snellen's box, when it is created, look here all of you. So this is the Snellen's E. So first of all, you create a box like this, right? This is a square with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Every direction 1, 2, 3, 4, 5. Okay. So you have, because every letter is fitting into the square with these 5 small squares. It is always therefore 5 times of the minimum angle of resolution. Okay? So it has 5 limbs. Just remember this. 1, 2, 3. So you just understand the basic here, why it is 5 times. So why it is every letter. If I am making a Landolt C, when the patient is illiterate, everybody knows he cannot read, means that you generally show him, okay, where is this C or ye gola kahan khul raha? This is how you ask the patient, isn't it? So this again is fitted in the same square with the same divided into 5 small squares. So it is the same 1 minute and 5 minutes. 1 minute and overall is always 5 minutes. Okay. So this is the explanation. Tell me something here. So when I say 6 by 60, after 6 by 60, suppose your patient is sitting at 6 meters and cannot read even the uppermost E letter. What will you next do? So if he cannot read 6 by 60, you are now going to put him make him sit in a nearer distance. Understand? So now from 6 meters, you ask him to sit at, okay, 5 meters. Then it could be coming to 1 meter, right? So generally you will ask him to first, okay, 6 meters pe you have checked it. He is not able to read. Make the distance shorter. 5 meter, 4 meter, 3 meter, till you come to 1 meter. That means, and if at 1 meter he is able to read, so now his acuity becomes 1 by 60. Isn't it? Or it could be 3 by 60 or 5 by 60, depending upon at what distance he is able to read. So, did you understand? 6 by 60 is one thing, then it could be 5 by 60, 4 by 60, 3 meters pe, and finally 1 meter pe 1 by 60. Suppose even at 1 meter he is not able to see the letter E. What next is the measurement? Then we are going to ask him to count the fingers. So that is, then we say the visual acuity is finger count. Okay. So finger count is generally at 1 meter we are doing. And if he is not able to count the fingers, then we are just moving the hand and checking where there is perception or he can perceive the hand movement or not. That becomes a hand movement. If this is also not there, then we are going to check the PL and PR. I think it's clear. So what is the minimum vision in a Snellen's box? On the Snellen's acuity chart, what is the minimum vision? Minimum is 1 by 60 will become the minimum visual acuity on Snellen's chart. Right? And which is the best acuity? When he can read this, come back here, think yourself, he's sitting at 6 meters and he's reading a 6 by 6 is one of the normal acuity. He can have a better than that acuity, means he can have 6 by 5. And that can go up to, actually some people have 6/4 or 6/3. So this becomes the best equity. Very rare to happen that. 6/5 is common. 6/5 is common, but going to 6/3 is very rare. Normal we will always consider is 6/6 only. Right? Understood now? So this is how you are going to document the visual acuity, and what we are measuring here is the form sense. Now we talk about what is hyper-acuity, or write down what do we mean by hyper-acuity. Hyper-acuity is also called stereo-acuity, or you can call it vernier acuity, discriminating acuity or vernier acuity. What is this? This is actually measuring the resolution power of your, resolution performance of your eye. Okay, so write down it measures the resolution performance of our eye. Right. That means whether how is your eye able to perceive two near objects, right, which are very near, right? So if we are going to look at this slide, we'll understand what is a hyperacuity, right? So 2 points which are very near, but little bit of you can say the difference. This is what is angle of displacement, right? So very near points, am I able to really perceive it as 2 points, different points, or it is too near for me? You understand what I'm saying? So that means if this angle of displacement is lesser and I can make it out, these are 2 points, compared to it is more. The same here, is it lesser or more? So which one is a better equity? When the angle of displacement is lesser and I am able to make out that these are 2 points. So actually this hyper-equity means it's an ability to find the 2 nearest points and see them separately, isn't it? So this is going to depend on the spacing of the retinal receptors. Just note down, it is governed by spacing of retinal receptors. And very important, a person should have 3D vision. Okay, that means all the grades of binocular single vision must be present in this patient to have the hyper-acuity or good resolution power, right? So it needs 3D vision. These are the 2 points you will remember. And what is the normal value? This is a little additional point. It has not been asked in the exam, but we should know it. And what is the normal value? Normally, the resolution of our eye, that is actually, you have to understand this way, that for normal humans, it is around 2 to 5 arc seconds. Okay. So this is not in minutes, we are now in seconds. So this is 2 to 5 arc seconds. So what is the resolution of your eye? We will just learn this. Resolution of eye here is, if you talk about just like in megapixels, we will learn it as 576 megapixels. Just imagine. Okay. So this is the resolution of your eye. Compare it with any better camera. It is much more than, right? So it is 576 megapixels. Next we talk about is how are you going to see this form sense of visual acuity? We have already learned a few things here. One, that is, so now let us learn the visual acuity assessment. If the patient is an adult or school-going children, right, who can read. What did we learn? That we can go for, first was Snellen's chart, right? And in Snellen's chart also, you should also know for, we will mention here, this is for the far vision. And Snellen's can also be for the near vision, both. So if you want to write here, you can write here near vision, but I'll just be mentioning the near vision charts. And secondly, we have to know what is Logmar chart. This is another chart which can be used. Logmar, we generally take the in the log units, that is logMAR chart is also called ETDRS chart. Okay? So this is your logMAR or ETDRS chart. And if the patient, so what is logMAR of ETDRS? Let's first discuss that otherwise. If you are going to look at a Snellen's chart, look here. If you look here, can you see one line? The first line is only one letter, then two letters, then 3 and 4, and this keeps on. There's a difference of letter in each line, right? Now, when we are talking about logMAR or ETDRS chart, it is fixed number of letters in each line. Look here or look here. So it is always a fixed number of letters in each line. And this test, so what are the points you will remember? Write it yourself. Number 1, this test is generally done at 4 meters distance. And very, very important benefit of this is that this excludes any factor of crowding phenomenon. It excludes which is factor of or avoids crowding phenomenon. What does this mean, all of you? I think I'm going to explain it to you in the amblyopia topic as well. So, a crowding phenomenon means that whenever the eye is amblyopic, the same letter in a Snellen's box which you cannot read in the Snellen's line, when it is presented independently, one can read it. So, it is difficult to read when it is series of letters, something like this. Okay, so that is why when the number of letters are same, this crowding phenomenon factor is generally negated. So, this is your, it is done at 4 meters and it is considered the most accurate method of checking the visual acuity. Please remember this. So, it is more accurate than even the Snellen's chart. If the patient is illiterate, we can note down Landolt broken ring test. This is Landolt's broken ring test. This one, you just have to be, be familiar with the names. Understanding will not be a problem. Only what is broken ring test or what is this? So just be familiar with the names. If you read it 2-3 times, you will understand. So this is Landolt's, it is LAN, sorry. Landolt's broken ring test. Another could be when you are checking the direction of E. We can call it tumbling E test. This is called tumbling E test. So these are, keep writing please. I'm writing on the slide. You all also keep writing. These are mainly for illiterate patients who cannot read the letters. Otherwise, we have letters, Hindi letters also and English letters also. Coming to the near vision. The near vision chart, generally what we are, write down for near vision. We can go for the Giger's chart, which is most commonly used. Then I told you Snellen's is also an option. Roman, again it is the names, okay? And you can even get an ETDRS or ETDRS version or logMAR version of for near as well. So near vision is tested with these, where we ask the patient to keep this near chart at a reading distance, and then we are checking whether he is able to read the smallest line or not. Okay, so this is your ETDRS or logMAR version of for near vision is also available. So what did you learn with me? For near vision, one was Giger, second is Snellen's, then Roman's, and the near version of logMAR and ETDRS. Okay? So this is how you have checked the visual field acuity. But this was for adults and school-going children. Now we have to also consider a few different age groups, how to check the visual acuity. So next we take the age group where the child is less than 1 year. Okay? So when the child is less than 1 year, what are the tests that you can go for? First is preferential acuity test. So in newborns and neonates or less than 1 year child, preferential acuity test is what? You are showing some cards to the child and whether he is preferring to look at it. That is what the test itself is telling you, explaining you the method, right? So preferential acuity test by Teller's chart. Just know, actually there's a long list of different tests. We have to pick up the most important and learn it. So I'm going little slow here so that you all are clear. So this is your preferential acuity test. Then Second would be your I'll just show you what is a teller's card. First, let us read this list. Optokinetic drum test. So optokinetic drum, you have learnt it in your neuro-optha also, that how it is a drum with a black and white stripes. Hai na? Okay, let's see it only then. See this one. So this is an optokinetic drum. It has a black and white stripes. Can you see that? Okay. So optokinetic drum is generally rotating. So it will attract the child and the child is going to look at the drum. So basic if the visual pathway is working or not working. This is what the main purpose is, to know whether you can see something or not. So to understand that, when the child is made to see this drum, what do I see? I am going to, if it is rotating, I am going to see the optokinetic nystagmus in the child's eye. So this is another method of seeing or assessing the vision in a child. Okay, it all has to be objective. We all know a small child cannot help you with any subjective test. What is subjective test? When the patient is participating, and if the patient is not participating at all, it is a objective test. Okay, instead of this, we can also have a drum with the dots, and when there is a drum with the dots, we call it CAD4 drum. Just be familiar with the name as I told you. Otherwise, if nothing is working, you can go for visual evoke potential or visual evoke response. So this is one of the electrodiagnostic tests in the retina, where you are going to see the activity from ganglion cell layer to the visual cortex. Okay, so the activity of ganglion cell layer till the visual cortex. This electrical activity can be recorded by showing a flash of light to the patient's eye. Okay, so this way we are able to, if it's just the flash, we will at least be able to know whether the visual pathway is working or not. And if we are showing some particular pattern, we are trying to assess the visual acuity in little more detail. Okay, so what was the first one? Preferential looking test, then it was optokinetic, and the third is your VER. What is 124 milliseconds? This is the time normally the impulse takes to travel. That means when the light is falling in your eye on the retina, the impulse to reach the visual cortex is 124 milliseconds. Now this is important. It was one of your questions. So we are going to learn it. That's why it is here. Right? Okay. So this was when the child is less than. Let's also see what is Teller's chart. See, this is the Teller's chart. Can you see these are the spacings and the lines? So what minimum spacing the child is attracted to or will give us the idea of the visual acuity. So here the spacings, the lines are a little wider, then it will become more narrow. So what is the spatial frequency which the child can detect? This will help me to assess the visual acuity of the child. Right? This is Teller's chart. Similarly, we have Keeler's chart, which looks something like this. We don't need to go to the details what is written. This Keeler is also used for the preferential looking test. So there is a circular patch to avoid any identification of the grating by its edges. That is why there is a circular patch. So these details are not much needed. Just know the name. One is Teller's, one is Keeler's. Please just understand the names. Know the names. Okay, we come to the next group of patient is preschool. Okay, the child is bigger but still not in school. We can go for some tests, subjective tests, right? What are these? One is Cardiff acuity test. So Cardiff can be both subjective and objective. So what is Cardiff test? First of all, let's see that. So Cardiff acuity test can be preferential looking, based on preferential looking if the child is very small and cannot respond, or in an older child it can be an objective test. For example, you are showing this card and it is just engraved with these designs. So is the child attracted to the design in this whole big card? Is he attracted to that figure which is engraved? That means he has some visual acuity. But if suppose the child is elder, little bigger, so you can ask what is made there? Is it a fish? Is it a car? So this will also help us to assess the visual acuity of the patient. Okay? So Cardiff acuity can be both objective or subjective. What is the next one? Sheridan-Gardner test is nothing but 4 letters HOTV are written in different sizes. And you have to see whether the patient is able to read or not, the child is able to read or not. So we have made the child comfortable by only giving these 4 letters, which is called Sheridan-Gardner test or 4 letters. So Sheridan-Gardner is a famous name and you should have an idea, okay? What is Sheridan-Gardner test? Next can be Allen's test card again for the preschool only. So what is this Allen's test card, where you are getting the different pictures and the patient is asked whether he can see what is made in this. So you can identify the picture. That is called Allen test cards. Let's see a list. So it was Sheridan, Gardner, Allen picture. Now we talk about what is Steicar test. So if the child is mentally retarded, it is recommended to go for this test, that is Steicar test. What is Steicar? So Steicar here stands for Screening Test for Young Children and Retarded. It is screening test for young children and retarded. That is called Steicar test. So what you do here is, the figures are made here in front, is shown in front in the card, and the child is also given some figures in his hand, and he has to just match that figure with the one in front of him. So whatever figure, suppose he is holding a card with an apple, he has to match that what he is seeing here, where is that in this particular chart. Okay, so that is what is Steicar test, right? So it is done at a distance of 10 to 20 foot. Again, too many details are not needed. I would just request you to listen to what I'm just saying is, you just match the cards. This is what is Steicar test. Okay, so that was about your visual acuity assessment for adults and school going, preschool going, and also less than 1 year. So now we are very, very pro to understand how do we assess the visual acuity, right? That was form sense. Now what are you looking at present is a pinhole. So you can see the small opening in this black occluder. So this is not an occluder, this is a pinhole. What is pinhole doing? It is cutting all the peripheral light rays and only the central light rays can pass. So pinhole test is, once you have done the refraction of the patient, or you want to just do the pinhole test and see, looking through the pinhole, is the vision becoming better? I hope you're writing. If the vision is becoming better, that means he has some refractive error which needs to be treated. Okay, because when you are cutting the peripheral light rays, the depth of your vision of focus becomes better, right? So please understand this, that any visual pinhole test includes what? It is mainly your seeing whether it is becoming better or is it becoming worse. So now we come to the second situation where vision is becoming lesser. Visual acuity or vision becomes worse on looking. So common sense, when can that happen? Any central problem, central opacities or macular lesions, isn't it? So any central opacities, whether it is corneal, whether it is lenticular, it will definitely decrease the vision, or it could be any macular disease, right? So this is what is called pinhole test. Now what are the exam questions apart from this that has been asked is, what is the size of the pinhole? So you will answer, size of pinhole can be 1 mm or sometimes it can be 1.2 mm. Both are correct. 1 millimeter or 1 millimeter or 1.2 millimeter. So see, this is what the pinhole is doing. It is cutting all the peripheral rays and only the central rays are focused on the retina. What is this now? We have learnt it in our lens chapter also, that this is a stenopic slit. This time the lens has got a long slit here. We call it stenopic slit. Okay. So talking about stenopic slit, the first thing they will ask you is, what is the size of the stenopic slit? Again, you are going to say this is, width is 1 millimeter and the length here will be 15 millimeters. Okay. So again, the size, the width you have to mention as 1 millimeter. Pinhole also, it was 1 millimeter, 1.2. Now, what is the role of using the slit? Okay, one we have already learned is Fincham's test, where you're passing the slit and seeing whether the halos are breaking or not. In case of colored halos, to see whether it is due to cataract or due to acute congestive glaucoma. We don't do so regularly this test, but yes, you have to know it at your level, it is asked. Come to what is the next we can do? We have to decide about the axis of astigmatism, right? Or you want to know At what, so you have to assess the visual acuity by using this slit, rotating it and trying to find out where the patient can see most clearly or not. So generally it is done to determine the site of iridectomy. Determine the site of iridectomy. If I have to do an iridectomy, I should be knowing where the vision is best. Also, it helps for determining the axis in astigmatism. So these are some rough assessments, of course, but you should know what the synovic slit is used for, can be used for, right? Okay. We were talking about assessing the visual acuity in a newborn child or in the child less than 1 year by, we talked about optokinetic nystagmus, or we could talk about visual evoke potential. We also talked about Teller's preferential looking test, correct? What is the visual acuity in a newborn child? So this is another interesting question. So if I talk about visual acuity, please note down it is less than 6/60. What was your exam question? I'll just let you know. So in a newborn child, it is, you will say the vision in newborn is less than 6/60. And why it is so? Small eye. So what is the refractive error? This has been one question. What is the refractive error in a newborn? You will say due to hypermetropia. So the eye is small. A smaller eye will have what? Hypermetropia. Power will be less. And also foveal reflex is not formed yet, right? So foveal reflex not formed means there is immature fovea. And because of this immature fovea, you are getting such a less vision. Now as the child grows, the eye is going to grow, fovea is going to mature, and in a normal circumstance, when will this vision become 6/6? So when is this vision going to become 6/6? This was your exam question. Make a cue there, all of you. We will answer at 6 years of age. So we expect a vision of 6/6, not in a 4-year-old child. Please remember that when you are getting the child tested for the vision, don't expect a 6/6 vision. That is expected to come from 6 years onwards. Correct? Okay. If I'm going to show bright light in front of the eye, your eye, will you blink? Yes. This is called Meniere's reflex. So in a small child, sometimes to assess whether the visual pathway is working or not, we can do the same. And this test is, we call it Meniere's reflex. So please remember that this is also going to be depicted only when the fovea is developed. Okay, so this will be by 5 months of age. We can see what is Meniere's reflex. If you want to write down when there is a blinking on showing a bright light in front of the eye. So blinking when the torch is near. So as you put the torch nearer, the patient is going to blink. So this is called Meniere's reflex. Got it? Yeah. We were talking about contrast sensitivity. So first of all, what is a contrast sensitivity? How do you define contrast sensitivity? All of you note down. We will say that it is the ability to distinguish any object against its background. Ability to distinguish any object against its background. Okay, this is what is called contrast sensitivity. What they will ask you is how to test it. Before that, is there any situation where vision is fine, 6/6, but only the contrast sensitivity is decreasing? Yes. So write down normal vision, but lesser contrast sensitivity with decreased contrast sensitivity. This, at your level, I will tell you 2 reasons or causes where we have to know. One is very important, that is amblyopia. So one cause we are going to learn amblyopia, and another learn it that it can happen in some optic neuropathies. Optic neuropathies. Good. We next talk about is how do you test the contrast sensitivity. So what are the tests? Again, as I told you, you have to be familiar with the names. Generally, the details are not asked, but yes, we'll know how to do the test. Note down. First, what you're looking at, this is what is Pelly-Robson. This one is the most common or famous name you have to remember, okay? Contrast sensitivity letter chart. This is the contrast sensitivity letter chart. So this letter chart, as you can see, as the contrast is decreasing, how much we are able to read. I think this is self-explanatory. So this is a contrast sensitivity letter chart. Pelly-Robson, number 1. We come to the second test that we can go for is these. Are the different lines? Are you able to see those lines separately? This is called, just again the name please, Arden gratings. These are Arden gratings. Okay. We come to the third one. What is this? Can you see there are different boxes and the different contrast sensitivity and different spatial arrangements are there in each box. So, and this has to be defined as up, this is your left, this is your right. So, the patient is asked to describe in each box. This is called FACT test. This is a functional acuity contrast test. In short, we write it as FACT. Functional acuity contrast test. Okay, so these are the Sanyo's gratings of different contrast sensitivity and spatial arrangement. So this is again, name please, this is enough. So it is actually telling us a functional visual acuity. Now what is this? This is generally done for illiterates and it's a computerized method where the patient is told to click at the box where he can see these gratings. And that grating, spatial arrangement and contrast sensitivity will keep varying. So in this case, if it is normal, he should click here. So where he is clicking here, his right, left or central, whatever. And different gratings are being presented to him. Okay. So this is called sparks. What is sparks? Number 4. What is the sparks status? Spieth-Richman. Okay. This is Spieth-Richman contrast sensitivity test. Spieth-Richman contrast sensitivity test. This is for illiterates. As I just explained you, it's a computerized method where the patient has to click at the box where he can just see the grating, because he may not be able to tell right, left and describe it. Just wherever he is able to visualize the grating, he has to click that box. Okay. So this is your sparks test. So these are some tests for contrast sensitivity. One more interesting, I don't know whether they haven't asked you this, but we are always supposed to know some extra points. So just remember that when you're talking about contrast sensitivity measurements, it can be very helpful for glaucoma patients also who are not manifesting with any visual field change, but we still doubt that there is a glaucoma, because visual field changes will appear only when appreciable amount of damage has occurred. So before that, if you want to see, so even contrast sensitivity measurements are helpful. Okay, if you want, you can note down. So that was about, so it's not a time pass here. So contrast sensitivity is helping in early diagnosis of glaucoma as well. We next talk about the color sense. So when you say color sense, when can you, at what age you start perceiving the color? Color perception will happen when the fovea is formed. And fovea starts forming from 6 weeks and is mature till 6 months. Right? So your color perception starts by, just remember like this, that the color perception generally color sense will starts by earliest from 3 months. Okay. And this is also an important information where the question is asked. I have repeated it earlier also, that fovea forms from 6 weeks, right? Okay, 1.5 months. Padha tha na, 2 starts forming and is matured by 5 to 6 months. This was called foveal reflex formation, right? So this is also asked in the exam, fovea maturation or foveal reflex formation. And color sense starts earliest by 3 months. Okay, so let's talk a little bit more about color sense. Everybody knows about Vibgyor, right? So whenever the white light is dispersed or scattering of the light is happening, you're getting these colors. And if you note down, the more the wavelength, lesser is the scattering, and that is why you're getting the different colors because of the different wavelengths of the different colors, right? So this dispersion or scattering is creating this Vibgyor. That everybody knows this. G is mainly green color is considered central. After that is all your longer wavelengths, and before that is shorter wavelength. Now when you say more shorter, it becomes what? Ultraviolet, isn't it? UV rays. And after that, this will become infrared. Now this is a very basic information, and many of you must be thinking, why is ma'am talking all this? A little bit more related to the eye here. UV rays can be A, B or C, isn't it? We know this: UVA, UVB and UVC. Now A rays are generally the shortest wavelength rays. These are mainly, we are saying that, absorbed by the lens. Just remember this. A normal lens absorbs this, and this is the reason, I hope you're writing, this is the reason that when you are operating on a patient of cataract and removing the lens, he may see more of the blue color, right? That is why there are IOLs which absorb blue color so that the patient is not disturbed much. Okay, so that was one clinical significance here. So you should all know that lens majorly absorbs the UVA rays. Now coming to B and C, it is mainly absorbed by cornea. Now UVB rays has a special importance here. We have learnt it earlier also. So what does too much of UVB ray can cause in your eye? I am repeating this, I think, but reminding you all about pterygium. And UVB can also cause, I have discussed this earlier also, I will not take the details here. Just remember snow blindness, which is also called photophthalmia or photokeratitis. Okay, photophthalmia, or we can also call it photokeratitis. And what does infrared ray cause? We have written this in our earlier notes. No doubt, infrared rays will lead to your photoretinitis. When you're looking directly at the solar eclipse, remember, we've discussed this, where there is a macular burn leading to macular scar. That is your photoretinitis. So a little bit about the color and VIBGYOR and importance of this VIBGYOR and how this VIBGYOR is formed by scattering of the white light. Now coming to how are we able to see and perceive this VIBGYOR? In our eye, there are three types. So there is a trichromatic theory. We are now believing it. So there are two theories. One is trichromatic and second is the opponent theory. We generally follow the trichromatic theory now, which is given by the young Helmholtz. You should know the name of the scientist. Helmholtz theory, we also call this as Helmholtz theory. Right. So young Helmholtz has given this theory that you all know it is the cones which are responsible for the color and not the rods. So the cones, we have three types of cones. Longer cones, larger ones, then medium size and small cones. And accordingly, for the long wavelength, it is the large cones. Right? And this is for the green, it is the medium size cones. And these are the smaller cones for the blue color. And it is the combination of all three which is actually responsible for the different colors that we perceive. This is a trichromatic theory. Simple. Large cones, longer wavelength, red. Medium, green. And small cones, your blue color. Okay. So these are the three primary colors, red, blue and green. Okay. Now, next that we have to understand is about color blindness. So if in a normal person, this is what is expected. What happens in color blindness? First of all, what are the types of color blindness? So please note down the classification here. If this patient has all three types of cones, but one is not working properly, there is a weakness. We call it anomaly, right? So if it is a red weakness, which is called protanomaly. When it is a green weakness, it is deutanomaly. And when it is blue weakness, we call it tritanomaly. Now, if one of the cones is totally absent, now this is your opia. You know? So when there is red blindness, no red cones, this is your protanopia. Green blindness is deuteranopia and blue blindness is tritanopia. Easy? And then we talk about is your monochromats kya hote hain then? Only one type of cone presenting and therefore the patient will just see different shades of grey. Okay? So this is your monochromats. Easy? So this is how you classify color blindness. What else we can talk about here is You may also classify the color blindness as congenital and acquired. Think with me. Acquired means there must be some disease which is causing problem in the color perception, right? And congenital is mainly autosomal recessive disease. Let's note down few points here. So when you talk about congenital color blindness, we all know because congenital color blindness is mainly seen in males, isn't it? So it is X-linked recessive disease, and therefore it is mainly the males who suffer from color blindness. Any other point that we want to say? So visual acuity may be normal because there is no disease as such. So in visual acuity, it is only the color part, perception part, or the color sense which can be affected in various ways you have just discussed. And hence the whole thing is stationary, it is not progressive. Whatever is done, it is not progressive. Here. So these are some points on color, congenital color blindness. Okay, it's an X-linked recessive disease. Primarily males are suffering from it, and generally the visual acuity is normal. Okay, and majority of the congenital blindness, you should know that it is mainly red-green blindness. Majority are mainly, primarily it is the red-green perception or the red-green blindness. We come to now think about with me about your acquired color blindness. When we talk about acquired color blindness, this definitely there is some disease because of which it is happening, common sense, right? And therefore visual acuity can be less and it can be progressive. Isn't it? It can be progressive. Now, there is a very interesting thing here. Tell me, suppose you are showing a color red to a patient of congenital color blindness. So when you show that red color, what does this patient will tell you? He is color blind. So what will he tell you? What color is he looking at? Can you think of it? What color is he looking at? Did he say it is grey? No, actually the interesting thing here you have to understand, a patient with a congenital color blindness, when he is given a red color, though he actually cannot see red, will answer you correctly as red. Because that name is a learned behavior. He has been taught that, okay, if you see this, this is red. Okay, but when you talk about an acquired color blindness, definitely the patient is not going to answer you a red. Because previously, he knows what red looks like. Okay, yeah. Now, when you talk about the diseases, the disease can be generally it can be either a retinal disease or an optic neuropathy which is causing color blindness. Now, there is a very interesting rule which is called Kollner's rule. So, Kollner's rule says that if it is an optic neuropathy, okay, any optic nerve disease or visual or other visual pathway is affected, or it is just the inner retina. Inner retina, you know, no? Inner retina, inner 6 layers, inner retina, then the major problem is in red and green. Okay, but vice versa, if it is the outer retinal disease, then it is generally blue-yellow blindness. Then it is generally your blue defect or blue-yellow defect. This is what is Kollner rule. Are there any exceptions to that rule? Yes, and you have to know that. The very interesting way of studying Kollner rule is in this flower. So the leaves which is showing you a red-green defect, trying to show is mainly optic nerve. Okay? Is mainly in optic nerve disease, whereas blue-yellow is mainly in the outer retinal disease. Now let's write the exceptions here on this one. So for outer retina, generally it is a blue-yellow except Stargardt's disease. We are going to learn Stargardt's in detail in your retina. So except Stargardt's disease. Okay? And similarly, coming to the exception for red-green is very important, except glaucoma. Just remember this. So you don't get a red-green blindness in glaucoma, though it is an optic neuropathy. Right? So this is your cardinal rule, and this is about your acquired color blindness. So we are going to learn about what are the different tests for screening, for classification and quantification of the color blindness. Let's see one by one. So this chart is one of the most common thing you have seen in an IOPD, and you should know about it. This is what is Ishihara chart. Okay. Right. So as you can see that the different numbers are given. So this chart generally in form of a book. It is in form of a book where different these plates, we call them different plates. So how many plates are generally there? It can be of two types, either 24 plated or it can be 38 plates. Now the minimum vision that is required to test this, it should be at least 6 by 18 and above. So vision should be more than 6 by 18. Right? And very important, please remember it. So initial first plate is always 12 and that is read by anyone, even if you are colorblind. Later, the next plates we see whether the patient can read or not. And the last are the plates which a normal person cannot read, but the colorblind can say something about it. So these plates, as you can see, if this patient is not able to read the less than 9 plates, okay, we then diagnose it as color blindness. So if the reading of the plate is less than 9 plates, this patient definitely is colorblind. And which color blindness are we talking about? Please remember, it diagnoses only red-green and not blue blindness. We are talking about red-green blindness. Please note down all these points. So Ishihara chart is mainly for screening purpose, okay? For the screening purpose, we are using it, and if it is less than 9 plates, the patient has color blindness and generally diagnoses red and green blindness. And in small children, you can use another one. This is called Hardy-Rand-Rittler test. Instead of Ishihara, this is also used for screening, and mainly the child can actually comment on the shapes. So we can go for this test as well, which is used for screening. Just know the name. The next one is, this is for quantification, okay? So quantification of color blindness, we can go for two main tests. One, what are you looking at? This one is also asked in the exam. It's important. This is Farnsworth-Munsell 100 hue test. Now what is very important and interesting here is 100 hue, the name is, but it is not 100 caps. These are only 85 caps. Just remember. And you have to just arrange it in the color progression. So in one series. So this is your Farnsworth-Munsell 100 hue test. Again, names are important. Too many details are not asked. Second one for quantification can be the Nagel's anemaloscope. This is also used, just know this, to quantify color blindness. And how do you classify the different color blindness? It is by Edridge's green lantern test. Again, only name please. So for classification, maybe even this is never asked yet. They have given you the question on Ishihara only, but you should know these names and be familiar with it. Okay. So Edridge green lantern test. Nothing more is needed here. Right. What is this? One of the another color vision testing, where this is called City University test. You have to match the peripheral with the centralmost. Okay, so this, just know the name. These are the different tests for color blindness, and that was all about color sense. Now let us solve a few questions on whatever you have just learned about the different visual perceptions, especially we are talking about form sense. Okay, so let's solve this. Let us read it together. What is this question? What is the angle which is subtended by the largest letter in the Snellen's chart on a person's eye who is reading it from a distance of 6 meters? So, all of you, largest angle subtended. What is the angle subtended by the, largest letter in the Snellen's box is which one? Everybody knows? Let's solve this. Which is the largest letter? Okay, largest letter matlab, we are talking about 6 by 60 visual acuity in the Snellen's box. Now, this largest letter When they are asking you, what is the question? Did you understand the question first? The patient is now at 6-meter distance. So you know this, that when I say angle of 5 minutes in 1 minute, that will be at a distance from 60 meters. Now the question is that from 60 meters we know the angle. What will be the angle subtended from 6 meters? Okay, so this is the question. Read it again. What is the angle subtended by the largest letter? Largest letter for the E letter, if you remember the Snellen's box. Okay, in the Snellen's chart, it could be any, but in our example it was E. It can be A also. Generally, these are the two common ones. So this E is what angle it is subtending from 6 meters is the question. From 60 meters we know. What is the angle subtended by 60 meters? Overall it will be 5 minutes and the margins will subtend 1 minute. So the minimum angle of resolution at the 60 meters is 1 minute. We know this. We have to find out what is the angle subtended at 6 meters. Isn't it? So how do you generally do that? Okay. So very simple technique is whatever visual acuity they ask you, just reverse it. So this becomes 60 by 6. Okay. So at 6, I am talking about how to calculate the minimum angle of resolution at 6 meters for any equity line. For any equity line, you just reverse the fraction. It was 6 by 60, make it 60 by 6. What is the minimum angle of resolution here? It becomes 10 minutes. Correct? But this is minimum angle. That means overall is always into 5. We have just learned that. That means our answer will become 50 minutes. Easy? So this was your exam question. Let's take for some other visual acuity so that you are even more clear. Now suppose we say, I ask you a question here, that what will be the angle subtended by 6 by 12 equity line from a distance of 6 meters, right? So here now, again, from a distance of 6 meters, what will be the minimum angle of resolution here? It will become 12 by 6, which is equal to 2 minutes. So this is the minimum angle of resolution at 6 meters. Now, total angle subtended into 5, which is equal to 10 minutes. Right? I hope this is absolutely clear to you. So this is what they had asked you in the exam. The exam question was on 6 by 60, not this one, but this is the way they can ask you. Come to the next question. Okay. A patient with a visual acuity of 6 by 24, okay, has to travel what distance? Means if at 6 meters I am able to read only 6 by 24 line, how much distance I should travel so that I can read 6 by 6. Okay, how to solve this one? Again, you have to think on the basis of minimum angle of resolution, right? So when you talk about minimum angle of resolution here, 6 by 24, right? So what is the minimum angle of resolution at 6 meters for 6 by 24 line? It is equal to 24 by 6, which is equal to 4 minutes. And what is the minimum angle of resolution for 6 by 6 line? It is of course 1 minute, right? So think yourself, let us solve it in this way, that now patient's visual acuity or minimum angle of resolution if at 4 minutes upon 1 minute, okay, will be equal to, what was that? At 6 meter. So at 6 meter, this patient is with a 6 by 24 visual acuity. At 6 meter, the minimum angle of resolution is 4 minutes. We have to find that at what distance it will become 1 minute. Are you getting my point? So we are just taking the fraction of 4 upon 1. 4 minute was at 6 meters. So we have to find out for 1 minute to make it 6 by 6. So will be at how many meters? So what is this value of x? Just cross multiply and see. So 4x is equal to 6. So x will be is equal to 6 by 4. Correct? So that amounts to 1.5 meters. Right? So when you say 1.5 meters, then this is the distance at which the minimum angle of resolution is 1 minute. Right? So he is already sitting at 6 meters. So how much distance he will travel, you have to subtract, then you get the answer. So it will be 6 meters minus 1.5 meters. This much he has to travel to get the 6 by 6 line. Right? So very simple. 6 by 24, think again with me. Visual acuity of 6 by 24 if this patient is having. So how do you calculate the angle subtended at 6 meters? At 24 meters it is 1 minute, but how to calculate it at 6 meters? You reverse the fraction and it becomes 4 minutes, this much we know. So at 6 meters if the minimum angle of resolution was 4 minutes, how much do we want it for making it 6 by 6? 1 minute. So if that was at 6 meters, at what distance it will become 1 minute? This is how you take it. Okay, so we are using the fraction of minimum angle of resolution and what is the distance, you get it, and then you solve it this way and you get the answer. So here what will be the answer? 6 minus 1.5, that is around 4.5 meters. He will have to travel to get a vision of 6. Then he is able to see the last line, that is 6 by 6. Correct? Okay. We come to the third question. Let's see this one. In this, what the patient is saying, a patient has, let's read together, a visual acuity of 6 by 36. Okay. At what distance will he be able to see the 6 by 6 Snellen's line? Again, it is almost the same thing, na? So 6 by 36 means at 6 meters, what will be the minimum angle of resolution? At 6 meters, this minimum angle of resolution is 36 by 6. 6 6 are 36. So it is 6 minutes, right? So when the minimum angle of resolution is 6 minutes, it is at 6 meters. We need a 1 minute minimum angle of resolution at what meters? Right? Simple. So again this becomes what is the value now? So cross multiply again. So it is 6x is equal to 6. So x will be equal to 1 meter. So at 1 meter distance, he will be able to read the last line. So this time he is not asking you how much he has to travel. That's the only difference from the previous question. It is at what distance it will happen. Then you don't have to subtract anything and you just have to answer like this. Right? Hope it is clear to you all. We'll talk about the next heading. Next heading, give the heading Purkinje images. So that was about the visual perceptions. Let's talk about Purkinje images. So what are Purkinje images? They are images, first understand with me. They are the images which are formed on the major refracting surface of your eye. So what is the major refracting surface of your eye? Cornea and lens. They are the major refracting surface. So please draw like this, it will be easier for you. So cornea and lens are the major refracting surface. Image formed on the anterior surface of cornea is Purkinje image 1. Okay. Then on the posterior surface, this becomes image 2. On the lens is image 3, anterior surface, and posterior surface is image 4. So this way in my style, this will become easier for you to understand. Okay. So once we know that these are the 4 Purkinje images, what are the questions they ask you? See, the slide is also showing you the same. I think mine one is little better to understand. So it is the same once first, second, third and fourth. Okay. So the first question is that which are the images absent in aphakia? Common sense, no lens, so no images. So absent in aphakia will be 3 and 4. Make a Q there. Second question is which image is inverted? I have discussed in introduction chapter also how the light rays focused by the cornea and the lens will be focusing at the nodal point, and here there is a crossing of the light rays, image gets inverted. So we will always learn this. It is the fourth image which is inverted. Fourth image is inverted. This was second question. And how many images are you going to get in a pseudophakia when you put an artificial lens? We will answer all four. So pseudophakia, your answer should be all four images. All four images are there. Right? The next question would be that what are the images in mature cataract? So we will learn that in mature cataract there are three images. The fourth is absent. Fourth is absent. Then they can also ask you about which Purkinje images you are using when you are doing a keratometry. Common sense, keratometry is used to see what? Anterior surface of the cornea. We are measuring the curvature. So this was also your exam question. For keratometry, we are using image 1. Right? Image 1 for keratometry. Right? Similarly, you can say assessing the depth of anterior chamber, it is 2 and 3 and so on. Generally, they have asked you this question. Right? So that was about Purkinje images. Okay. We next talk about a few instruments where they have asked you maximum questions is about direct and indirect ophthalmoscope. I'll be mentioning it more in the retina chapter also. We have talked about it in introduction also. Right? So this is what are you looking at? What is this? It's a direct ophthalmoscope. We have seen it in the introduction chapter. Direct ophthalmoscope. Okay, so when you say direct ophthalmoscope, you're taking it very close to the patient's eye like this, and you are seeing what? The retina. Retinoscope, is the retinoscope and ophthalmoscope the same thing? Absolutely not. Please remember, I have discussed this with you all. Retinoscope is an instrument for objective method of refraction. I'll show you that later in this chapter. But ophthalmoscope is for examining the retina. It is also called fundoscope. If you want to call it something else, it is fundoscope. What are the points they have asked you and you have to remember? First thing they have asked you, these are all cues, so I am putting the cues here itself, is what is the magnification of direct ophthalmoscope? Generally, we learn it as 15 times. Okay? Second question. Type of image formed, virtual and erect. Okay? So much of magnification with the virtual erect image, we are definitely wanting to see the central retina. Why? Think yourself, if magnification is more, field is going to be less. When you look through a magnifying glass, do you realize this? That whatever you are looking is magnified, then but the surrounding you are not able to see. So whenever magnification is more, field is always less. So please remember this. It is inverse. Magnification of field is inverse of magnification. Okay. So what is the field here at one time that I am able to see? So you can note down that field is actually inverse is equal to 1 upon magnification. So this field is how much here? We will learn 2 disc diameter. So these are all cues. 2 disc diameter. When we are talking about field, I'm so sorry. This is 2 disc diameter. So when you say 2 disc diameter, how much area are we talking about? 3 millimeters. 1 disc diameter is 1.5. So this is 3 millimeters. We are saying that at one time, this is the area that I can see. So we now know the field, we know the magnification, why we are using it, and what is the type of image form. Another question, very interesting, recently asked in an exam is that, okay, so which eye of examiner and which eye of the patient is used? So it's very, very simple common sense. If you are my patient, I have to see your right eye. I cannot look like this now. I will use my right eye. Okay, so it's always right and right, left and left. So it is same eye. Okay, right eye of examiner hai, for the patient can be examined by right eye of examiner. Remember this. So this was another question on direct ophthalmoscope. And how do you calculate the magnification of direct? If they ask you this, if the calculation of magnification in this is power upon 4. Whatever is the power upon 4. So power of I we are talking about. Okay. So when you say power of I, for a emetropic eye, what is the power? It is 60 diopters is taken as the power of I. We have learned this, have we? Did we talk about, okay, let's quickly revise this also, that it is generally 58 to 60 diopters, so we generally learn 60 diopters. So 60 upon 4, and this is what is 15 times that you have learned. Learning here that this is the magnification. I think these are the only possible questions they've asked you for direct. Now we talk about, I'll just revise the data and powers shortly. Coming to what is happening here. Let's see the other instrument to see the retina. So the patient, the examiner is wearing this headband, the light is coming out, he's holding a condensing lens here and he is looking at the patient. So this is what is indirect ophthalmoscopy. This is your indirect ophthalmoscopy. First of all, you should know this. What are the points to remember? Magnification, no, it's less, 3 times or 5 times. This is what is the magnification. Either it is 3 times or 5 times. So magnification is less means field is going to be more. Yes. So 1 time it is 8 disc diameter. That means 8 into 1.5 millimeters. And what is the type of image is another question. We will answer real and inverted. These are all your very important exam questions. So we have to know this. Then that means if it is field is more and magnification is less, what are we looking at is peripheral retina. So this is mainly used to see the peripheral retina. Another question they've asked you here is, where is the image formed when you're doing indirect ophthalmoscopy? Let's see this. So the light is coming from the patient's eye. I have to see his retina here is focused by the condensing lens. This is the image formed in ear between the examiner's eye and the lens that he's holding. So if I'm examining the patient, generally we do it properly when patient is lying down and we are at the head end. I'm holding the condensing lens here like this to see the clearly. Actually the image is formed in the ear between the lens and my eye. So this is aerial image which is formed. It is then going into the eye through these reflecting mirrors. Right? So this is how an indirect ophthalmoscope works. So this is also asked in the exam. Where is the image formed? It is between the lens and the examiner. Done? Okay. What about how to calculate the magnification of your indirect ophthalmoscope? To calculate the magnification here, we will calculate it as power of I upon power of the lens. Okay. And what is the condensing lens power we use? Even this has been your exam question. Q lagao. So any condensing lens actually for your information can range from 13 to 30. Easy to learn, 13 to 30. But commonest that we use is 20D. This was your exam question. So it can range from anything from 13 to 30 theoretically, but commonly what we use is a 20D lens. So suppose we are calculating here with 60 and 20D lens. If emetropic eye means the power is 60 and power of eye upon power of lens. So this will be 3 times. Correct? Yeah. Now suppose I tell you that this patient is not emetropic. He has a myopia of -5. Pay attention, this is very interesting. If there is a myopia of -5, what will be the power? M for M, myopia means more power. It will be 60 plus 5. So if my patient has a myopia of -5, it simply means his refractive power in the eye is 65 diopters. So now it will become 65 into 20. This will be my value of 9. And vice versa for hypermetropia. So keep this in mind. If suppose I would have told you that, okay, this patient is hypermetropic by +5. We denote it with plus. I'll just come to it again in detail about refractive errors, but we all know hypermetropia is less power. So here again, what we are doing here is, we are subtracting this instead of adding. So it becomes 55 upon 20 for a hypermetro. In this example, these are examples, right? So just remember this. These are some important informations and very commonly asked questions that you have to keep in mind. What about if I ask you that the slit lamp that you're using, what is the magnification here, that how to calculate this one? This is a usual instrument. It's like a bread and butter of the how to know the see the anterior segment and all, we cannot comment anything without a slit lamp, isn't it? So what is the magnification? It's simply, learn with me that the magnification formula is same, that is power of eye upon power of lens. Okay, but what you have to understand here, we will also multiply it with the, what is the slit lamp magnification. Just remember this. Okay, whatever value is coming, you have to multiply with slit lamp magnification. So this is the formula for calculating the magnification in slit lamp. So this one has not been asked yet. It's again an additional point. Okay, so our next heading is visual angles. Give the heading visual angles. So when you look at this diagram, let's first see what we are saying. Visual angles mean, first we have to understand what is angle alpha, what is angle kappa. So what is this blue line showing you? We will write later, we are first talking, okay? So all of you pay attention. What is this blue line? This is an imaginary line which is dividing the eyeball into two halves. And this is what is called optic axis. Correct? Now, the line that is passing through your fovea, the green one, is your visual axis. So this is your visual axis. Okay? The angle between blue and green, this is what is angle alpha. Right? Now, then we talk about what is angle kappa. So, first we will write this one. So, let's make this for ourselves to make things simple. So, this is the eyeball, an imaginary line which is crossing it into two halves. This is your optic axis. Then, fovea's little temporal, a line, everything is imaginary of course. And this is crossing like this. This is your visual axis. Ideally, it should be at intersection, should be at the nodal point. And this angle so formed is angle alpha. This is more accurate what I have drawn here. Right? So this is angle alpha. So what is angle alpha was your exam question. So what is angle alpha? It is angle between the optic axis and visual axis. Now it was seen it is very difficult to discern the center of the cornea through which the optic axis is passing and dividing the eyeball into two halves. So it was decided, let's take the center of the pupil. If you take the center of pupil, now the line which is dividing into two halves is called pupillary line. It is almost like optic axis, very slight difference. I'll just show you this slide. Let's make it here first. So now this line is your pupillary line or pupillary axis which is passing through center of pupil. Okay, and this is again your visual axis, and the angle that is formed on the cornea here, this is what is angle kappa. Okay, so what is angle kappa is not much different from alpha, and it's a very small angle of around 5 degrees. Very, very slight difference. So kappa alpha can be considered almost same. But if they ask you, you should know the difference. When we say kappa, it is an angle between pupillary line and visual axis. This is angle kappa at the cornea. So this is the visual axis passing through the fovea. Got it? If you look here, this pupillary axis, the red one is almost overlapping the blue one later. So it's almost the same, a slight difference. And now the angle between this red and the green. Green is the visual axis and red is the pupillary axis, becomes the angle kappa. Okay, so that becomes angle kappa. So once you know theoretically, okay, I'll define alpha as between optic axis and visual axis. Kappa is between pupillary line and visual axis. Okay, this is one way you will answer the question. The second thing is, you may ask you, why are we learning this? Why are these imaginary lines and what is the significance? So at our level, what significance we have to understand is, let's understand that. Now pay attention. If you're going to show, if I show this torchlight in front of your eye, okay, both your eyes are straight, okay? So what will happen, that the light is going to fall on the center, not exactly center, slightly nasal. In it is considered center only at the center of the pupil. Or if you want to understand this way, you are showing light in front of my eye If you are the examiner and you're showing the light in front of my eye, correct? So the light is falling not exactly centered, slightly nasally, slightly, because we all have a positive angle kappa. So first thing to understand here is that whenever the reflex is falling nasally, we call it a positive angle kappa. When reflex falls more temporally, we call it temporal from the center, it is called negative angle kappa. Okay, so when you say we have all emetropic person with a straight eyes will have what? A small positive angle kappa. Now suppose you show the light in front of the eye and the reflex is falling too much nasal. If the reflex, we will talk about it in squint again. If it is falling too much nasal, do you realize what will happen? Imagine yourself that you are examining the eye, showing the torchlight, and the reflex is nasal. If it is falling too much nasal means it feels as if the eye is out, though it is not out. Right? So this is large positive. Too much nasal means large positive kappa. The reflex is more nasally. And if the reflex falls more nasally, it indicates larger angle kappa. It looks as if the eye is out, though it is not. And this is what eye is out means exotropia, but it is not. So it's a pseudo exotropia. So we will call it pseudo exotropia. Okay. Now let's see the other way. The reflex when you showed in front of my eye is falling more temporally. If it falls temporally, what will it feel like? That the eye is going in, though it is not. So a large negative, temporally means negative kappa, correct? So large negative kappa means that means the reflex falls more temporally. So it feels as if the eye is in, but it is not. So it is called pseudo esotropia. So when you are listening to me for the first time, it may seem complicated, but it is not. Maybe you can listen 2-3 times to understand what I'm trying to put here. Or when you are going to solve the question around it, you will understand why I was talking like this. Now, then we talk about is when you say large positive angle kappa, here comes a point, it is seen in high hypermetropia. So, high hypermetropia can be a cause of pseudo squint, that is pseudo exotropia. And a large negative kappa is generally seen in high myopes. So, in high myopia, you may get a pseudo esotropia. So, these are the things you have to understand, that mainly whether the reflex is falling according to, when you are looking at the reflex, it is giving us an indication or a hint about the angle kappa of that patient, and we have to be aware of this, otherwise we are not going to diagnose the squint properly. Okay, so is it a large positive angle kappa or actually there is a squint? Of course, there are so many tests to diagnose whether there is squint or not, so we will have to go further on that. So we'll discuss this in the squint chapter. I gave you the basics here. So this was about your visual angles. Just know about what is alpha, what is kappa, and how it helps us to assess the cause of pseudo exo, pseudo eso. Right? Okay. Now we are having refractive errors. Next we talk about is refractive errors. So we know this basics. We start with first is myopia. Okay, what are the refractive errors if I ask you to list down? First, myopia, okay, then hypermetropia. What else will you say? Astigmatism. What else? Please don't answer presbyopia, it's not a refractive error. It's an error of accommodation. We have talked about it earlier also. So not presbyopia, we will say anisometropia. And lastly, we can learn aniconia. Anisometropia, aniconia. Okay, so these are the different refractive errors. One by one. First is myopia. Very simple, pay attention. M for M, myopia is that error in refractive error where the refractive power is more than required. So we all know that if you look at the eye here, the light rays should be falling nicely on the retina, then we are all happy and we can see nicely. This is your emetropic stage. Now, if the power in this eye is more than what is required, then what will happen? The bending of light rays are going to be more and it is going to focus even before reaching the retina. This is myopia. And when your refractive power is less than what is required in an emetropic state, then now your bending is not sufficient. If your bending is not sufficient, it is finally going to focus behind the retina. This is hypermetropia. Okay? So if we have understood, let's quickly write it. Myopia, M for M is more power. So more power in eye than required. Number 1. Right? Number 1. Number 2. Light rays, let's quickly make the diagram. Light rays are focused in front of the retina. Now we need the focusing. We need the focusing on the retina. So you have to decrease the power. How do you decrease the power? Concave lens to get the focusing here. How much do I need to decrease the power to focus on the retina? This is the measure of my myopia, how much I have to decrease the power. Therefore, myopia is always indicated as minus. How much I am decreasing. Got it? Okay, so once we know this, then once we know what is myopia, how do you classify this? We can classify it as it can be axial myopia. When the axial length is more, we call it axial myopia. More axial length. It can be curvature myopia where more power is actually due to more curvature of the cornea. This is more corneal curvature is curvature myopia. Then index myopia means this time it is more refractive index, right, of the lens mainly we are talking about. Fourth one, positional, okay, positional myopia. Positional myopia means any dislocation of the lens, anterior dislocation can lead to more power. These are the classifications of myopia. Then we talk about is how will the patient present. Patient is going to present with, we all know this, half of us are more than that are myopic. So blurred vision, for far, mainly for the far. So this is the complaint of the patient, blurring of vision for far or difficulty or diminution of vision for the far vision. And when you are examining this myopic patient, what are the other features we can see? Let's make a diagram and label it. So what do you see here? One by one, first is a long eye. Okay, so more axial length or long eye. Axial length is more. Right? Secondly, what you will see, because there is a stretching of the eyeball, there is thin sclera. Thirdly, what you see is deep anterior chamber. And what about the ciliary muscles that help in accommodation? Accommodation purpose is to increase the power of your eye. But your power is already too much, I don't require that much. That means your ciliary muscles are not working, taking rest, and they become weak and sometimes even atrophic. Okay, so no stimulus for accommodation means ciliary muscle atrophy are weak or they become later atrophy. They atrophy. Okay, so anything else I want to comment? Yes, retinal changes, especially in pathological myopia. What are the retinal changes of pathological myopia? We are going to learn in retina chapter. That is called pathological myopia. Whenever there are retinal changes, we call it pathological myopia. Right? And how are you going to manage myopia? Of course, myopia treatment will be either I use specs or I can use a contact lens or we can go for refractive surgeries. We are going to take all this in detail As of now, write this just. Okay, great. Next we talk about is hypermetropia. Our second error of refraction was hypermetropia. Before that, so this is what you see here, how the light rays are focused in front of the retina and how a concave lens helps it to focus on the retina. Simple. Talking about hypermetropia. So hypermetropia, what did we learn? Number one important point, the power is less than required. So power is less than required. This time eye is small, isn't it? Smaller eye, and light rays are focused behind the retina. I need the focusing on the retina. So I am going to increase the power with convex lenses. How much do I need to increase the power will be the measure of my hypermetropia, and therefore we always indicate hypermetropia as plus. How much we are increasing. Correct? Okay. Same as myopia, you can divide hypermetropia as hypermetropia can be axial when there is a smaller eye, less axial length. It can be curvature. Again, it is lesser curvature of the cornea, more flatter cornea. Index hypermetropia, index is decreasing due to old age. In old age. That could also be a cause. And fourth, then we talk about is positional. Positional, it is the posterior dislocation. So just understand everything. There is nothing to mug up. Okay. Now, once we know this, definitely the major refracting surfaces were cornea, lens, and the third major part is your axial lens. So we are mainly talking about these things only. Okay. Then we talk about that any hypermetropia very quickly can be divided as total hypermetropia, whatever is there in your eye. Okay. That can be first of all divided as latent and manifest. Now latent means it is due to the ciliary body tone. Now this due to ciliary body tone, this is around 1 diopters. Whereas when we talk about manifest will be again depending on is it facultative or is it. So HF is facultative hypermetropia or it can be absolute hypermetropia. So when do you call it as facultative? When you can overcome this hypermetropia by accommodation. When you can overcome by accommodation. We call it facultative. Means above the basic ciliary body tone. And then absolute means the one which cannot be. Okay. So this cannot be overcome. Overcome by accommodation. Just have an idea why it is divided, what is total hypermetropia. So do you understand total hypermetropia means when you have totally paralyzed the ciliary muscles? How can you do that? Through atropine. And now you are trying to find the amount of hypermetropia by giving the convex lenses. So the maximum convex lens which will give the best vision. Right? So that is maximum vision or best vision by the strongest convex lens will give you this total hypermetropia if you have put atropine. Make sense? Right? So you are putting atropine and then seeing what is the strongest convex lens that is being used for maximum visual acuity. Right? This is your giving the measure of total. And without atropine, that means you are not disturbing the ciliary body tone. And then when you are finding the strongest convex giving the maximum, this is this strongest convex lens giving maximum vision. This will be your manifest. Now in that manifest, if you have to find out what is the facultative and what is the absolute, For absolute, you just take the weakest convex lens which is giving the maximum visual. But rest can be taken care of by the accommodation. So simple, logical. So now weakest convex lens giving maximum, for weakest plus lens giving maximum visual acuity, isn't it? Or I'll write here, it is the weakest plus lens, convex lens, which is giving maximum visual acuity, means 6 by 6, whatever maximum vision that patient has, this is what is your giving you the measure of absolute hypermetropia. Okay? Okay. So once we know this much about hypermetropia, how will this patient present? A patient of hypermetropia, because do you understand, whenever there is a hypermetropia and you're not correcting, you're using more of your ciliary muscles. So the patient will have headache, eye strain, and these are what are called asthenopic symptoms. Okay. So these are asthenopia or asthenopic symptoms will be seen. And there will be difficulty for high hypermetropia especially. You will have difficulty for both far and near. Please be very, very clear about this. See, I didn't use the word far-sightedness and long-sightedness because it gives a very wrong impression that when you say long-sightedness, this is a difficulty in near. Difficulty purely in near is what is called presbyopia that we have already discussed, right? We'll discuss further. So, please remember, when you're talking about hypermetropia, we are talking about, it could be both, especially in hypermetropia, right? Okay. Then we talk about, once this patient is presenting with this, what are the on-examination findings? If this patient is accommodating too much and the hypermetropia is not corrected, if we start the ocular examination and we talk about ocular alignment, he can get an accommodative esotropia. Okay, number 1, that is convergent squint. Eso is convergent, tropia is squint. Because of excessive accommodation that is exerted, the eyes converge. You may ask me, why ma'am, why the eyes are converging? You have learned with me the near reflex. What are the components of near reflex? Convergence, meiosis, accommodation. So it is all coupled. So in these patients, if there is too much excessive accommodation, the eye will also converge as a part of it. Okay. So this is accommodative esotropia. Then you have to know another term, what is pseudomyopia. So when you say pseudomyopia, it is nothing but accommodation spasm. Okay. So the patient is having difficulty, is showing that it has more power in the eye, though actually it is due to excessive accommodation he is exerting. He is not myopic as such. So this is accommodative spasm. Right. So in that case, he will have a problem in even reading the near prints and the heart. So this is what is accommodative spasm. Just remember the term pseudomyopia, it was asked once. Okay. Then we talk about is, what are the other on-examination findings? Let's draw the diagram and learn it. Of course, the eye is small eye. Because this I'm making a bigger one, don't go on that, just for our convenience. So it's a small eye, and if it's a small eye, we also know that curvature here will be flatter, isn't it? When there is a flatter curvature, it is more radius of curvature. I hope you know this. Lesser curved means more radius of curvature. This can be seen, flatter cornea. Then shallow anterior chamber, narrow angles, which can be prone to closure. The angles may close, isn't it? So keep this in mind, these narrow angles can be prone to closure, and the lens is normal. So this is the main reason why the angle closure is a problem. And what are you going to get in the retina finding? Very interesting term. One is, I have discussed this in your neuroophtha, pseudopapillitis, where there is blurring of the margin is appreciated, but there is no papillitis. It is due to small eye, small lamina cribosa, and small size of the disc. Okay, that is called pseudopapillitis. So pseudopapillitis And second is the retina is typically very shiny, and this shiny retina is what is called, just know this, short silk retina. The term should be familiar to you. It is short silk retina. Right? So these are the on examination findings for hypermetropia. How will you treat it? So hypermetropia treatment, again, basics, we can give specs, you can give contact lens. If the patient is a fakey, you may give IOL implantation or refractive surgeries. Right? Okay. Coming to the specs correction, here I am going to give a convex lens, isn't it? Yeah. Whereas in myopia, we were giving concave. Now, there's another interesting and important exam question. Whenever you're using the glasses, whether it is convex, all of you who are myopes and you're using a minus or concave lens, right? Do you realize what is happening? That when you remove the specs, you see little larger than when you are with the specs. So a concave lens actually minifies the image. Okay? It minifies the image. Whereas a convex lens, when you're wearing convex lenses, it is magnifying the image. It magnifies the image. Right? And here comes a question. One diopter is responsible for 2% of change in the image size. Keep this in mind. Either it is minification or magnification, this is important. Another important point. Let's see this one. What happens when you take your if you're myopic and you're using a concave, what happens when you take your glasses near? And what happens when you take your glasses away? So I hope you all know that effective power, just note it down as well, effective power of concave lens is more when it is near the eye. Isn't it? And this effective, we are going to, in detail, we are going to also discuss this in contact lens topic. And an effective power of a convex lens will be more. So, plus lens we are talking about, right? So, this is more when it is away from the eye. How will you learn this? Or if you get confused, it's very simple. You all are familiar with Hindi movies. Do you see that Munimji sitting with a near glass, away, just hanging here at the tip of his nose? So why are you putting the reading glass away? Reading glasses are convex lenses. So the more you put away, the better you see, the better is your effective power of the lens. That is why you're not actually serious enough to go for an eye test and get your glasses changed. You're using the same glass. So now what to do, how to manage? You keep it away from the nose. So you'll never forget this, that a plus lens, effective power is more when it is away from the nose. Reading glasses are plus lenses only. And in a concave lens, it will be effective power is better when it is towards your eye. Okay? So away from the eye, effective power will be more in convex. Okay. So once we know these interesting facts, we talk about astigmatism. The third is astigmatism. When you say astigmatism, what is astigmatism? This time the power is not the same all around. If we take the two principal axes, there is difference of power between the two principal axes. So write down what is astigmatism. When I say difference of power means, you have learned with me, more the curvature, more is the refractive power. So here one axis is more curved than other. So power in one is more, other is less. It could be opposite also. Either the horizontal is curved more or vertical is curved more. So when the curvature is more, the power is more. When there is a difference in power in vertical and horizontal, this is what is called astigmatism. Got it? So please note down, it is difference of refractive power between two principal axes. Between two principal axes. This is what is astigmatism. Now, how do you classify astigmatism? So you can classify astigmatism in 4 different ways. Okay. So first way of classifying is if the difference between the two axes is such that one has no number and other is a plus number. Or vice versa, it could be one has no number, other is a minus number. Or it could be both are minus but they are different minus, -2, -3. Or both are plus but they are different plus. Or it could be 1 plus or 1 minus. Okay, don't get confused, I am coming back to the first one. So, when I say 0, that means one axis is emmetropic, which means focusing on the retina will happen, but the other axis, the focusing is behind the retina. This is called simple hypermetropic astigmatism. Simple hypermetropic. Now, when one is emmetropic, other is myopic, this is simple myopic astigmatism. This becomes compound myopic. This becomes compound hypermetropic, and this is mixed. One eye plus, one eye minus, this is mixed astigmatism. So, one way of classifying astigmatism is this. Let's see the slides here. So, first of all, okay, we are looking at hypermetropia where focusing is behind. I used a convex lens, now it is focused on the retina. Okay, then we will look at this one where one axis is more curved than the other. This is what is astigmatism. And when there is an astigmatism, yes, you should note down this, that there is not a single focal point but more than one. So, multiple focal points is giving this type of blurred vision. So, there are multiple focal points and this is giving the blurred vision in the patient. This is how astigmatism patient will look at this letter A. Right? So, please note down there is multiple focal points, more than one. This one is what I just discussed with you. If one eye is focused, another is focused in front, one axis is focused on the retina, other is in front of the retina. This is simple myopic. When one is behind the retina and other is on the retina, this is simple hypermetropic. I hope it's absolutely very, very clear. Then what is compound myopic means both are in front. Compound hypermetropic, both are behind. And mixed means one is in front and one is behind. Okay. What is the second way of classifying astigmatism? So, majority of the time, the principal axis will be one at 90 and one at 180. You can call it 0 or 180, whatever. So, one at 90, one at 180, and it is perpendicular to each other. Now, if the two axes are still perpendicular to each other, but they are not at 180 and 90, this is what is called oblique astigmatism. So, the angle between the two is 90 degree, but they are not at 90, 180 axis. This is oblique astigmatism. And if the angle is also less than 90, now this is called bi-oblique astigmatism. Now this is bi-oblique astigmatism. Okay, so this is another way. This one becomes irregular. We just call it regular here. And this is oblique astigmatism and this is bi-oblique when the angle between the two axes is less. Right? Okay, then we come to the third type. What is regular astigmatism and what is irregular? Another way of classifying is regular or irregular. So, think this way. In a single axis, suppose I write here -2 and I write here -3. So, do you realize that 90 degree if it is -2, everywhere it has to be -2. Here also, here also, here also. So, when the power is constant in a single axis, this is your regular astigmatism. Got it? But suppose that even in the single axis there is a variation. Now this is what is irregular astigmatism. Even in the single axis there is a variation. This is where do you learn irregular astigmatism? We will answer, we learn it in keratoconus. Irregular, we learn it in keratoconus. Okay, so this was the third way, regular, irregular. What about the fourth way of classifying? With the rule, against the rule. What do we mean by with the rule and why do you call it with the rule and why do we call this against the rule? With the rule means that it is the vertical which is more, okay. So with the rule means it is the vertical which is more curved than the horizontal, right? So when vertical is more curved, this is with the rule. And if horizontal is more curved, more power in the horizontal than the vertical, now this is called against the rule astigmatism. Now why we call it against the rule or with the rule then? This is because what is expected is due to pressure of your lid, it is the vertical axis which should be more curved. So if the vertical is getting, so there can be normally a 0.25 difference between the two axes, which is almost normal in the eye. But suppose there is a significant difference and it is the vertical which is more curved, it is said to follow the rule. So that is why with the rule. And this one is against the rule. Got it? Okay. So once you know what are these different types of astigmatism, now comes a few very interesting questions here. So this is what you're looking at. This is with the rule where the vertical is more and here the horizontal is more. This is no astigmatism. This is what we mean by regular, and this becomes irregular astigmatism. I hope you can appreciate. Even in single axis there is a variation. Okay, so once we know this, let us see if you can answer this. All of you try to answer this, that what is the type of astigmatism? I'm giving few examples. Number one is this one. Example number one. What is the type of astigmatism here? In 2, what is the type of astigmatism here? What is the type of astigmatism here? Can we answer this? It would have been more fun if I could have directly talked to you. But anyway, if I say example number 1, -3, -2, which is more power? Don't use your algebra here, okay? So, minus simply on a retinoscopy, if you make this 2 lines vertical and horizontal, when you write minus, it means we are talking about myopia. When we write plus, we are talking about hypermetropia. So, when I am saying it is minus, what did you understand here? That power is more for vertical than, so myopia is minus, so more power here, less power compared to the vertical. So, this becomes with the rule astigmatism. And if you see here, it is vice versa. This is against the rule astigmatism. And what about this one? See carefully. +3, +2. Plus is hypermetropia, which means less power. So, the more you are going in plus, you remember? We will subtract from the total power. That means +3 means if your eye was emetropic is 60 diopters. +3 matlab what is the power? 60 minus 3. Whereas -3 means what is the power? 60 plus 3, because this is myopia. So here this is +2. So therefore this is with the rule because power in the vertical is more. But when you talk about hypermetropia, power on the vertical is this and power on the horizontal is this. So which is less now? So vertical is less than horizontal. So this becomes against the rule astigmatism. I hope you are very, very clear now. 0 means what? 60. Isn't it? Okay, take another example. What is the type of astigmatism out here? Is it with the rule, against the rule? So 0 is 60. I just gave you the hint. This will be 60 minus 3. This is already 60. So it is with the rule astigmatism. Right? And what about this one? Tell me. Again, this is 60, but this is 60 plus 6. It is minus means myopia. So it is with the rule astigmatism. I hope it is very, very clear to you how to see which power is more and then declare with the rule or against the rule astigmatism. Right? And can you also answer me this one, all of you? What type of astigmatism is this one? So, 10, 9, 8, fast. What type of astigmatism is this one? Can we talk about this? This is not astigmatism at all. Both the axes, same power, there is no astigmatism. Okay? So, keep this in mind. Okay, very quickly, according to the classification, the first one that we learn, can we also comment on this? That example number 1 is both are minus, so it is compound myopic. Both are minus again, compound myopic. Both are plus, compound hypermetropic. Isn't it? Here what will you answer? This is simple hypermetropic and this is simple myopic. Right? Great. So these are the questions they can ask you, that which is which type of astigmatism. according to classification number 1 and this classification with the rule and against the rule. The question has been asked, these examples are important for you, right? How do you generally treat astigmatism? So generally a patient of astigmatism is going to present with a lot of eye strain and blurring of the letters as you saw. Okay, so that will be the main complaint. The astigmatism may not clear vision, blurred vision, lot of eye strain and headache can be a complaint. Now in that case, how do we treat it? You have to give a correction more in one axis than the other. So the treatment is mainly, it is the cylindrical lenses. Okay, cylindrical correction in the specs is given to treat astigmatism. And if we talk about contact lens, for contact lens we use toric contact lens when there is a cylindrical correction, and similarly we can use toric IOLs if needed, right? And of course we have a set of refractive surgeries which can correct astigmatism. We'll talk about that. Right, so that was astigmatism. What is next error we learnt in our list was anisometropia. What is anisometropia? Difference of power between the two eye. I have actually mentioned this in the introduction. Difference of power between two eye of more than 2.5 diopters. This is what is anisometropia. Okay, so what is anisometropia? When there is a difference of refractive power between two eyes of more than 2.5 diopters. Again, you have to just correct the refractive error in each. What is anisoconia then? What is anisoconia? Note down, anisoconia is difference of image size between two eyes. Right? So it is difference of image size between two eyes. Right, all of you? So if this image, of course, this when there is a difference of power, there can be difference of image size as well. So when there is a difference of image size between two eyes, we call it anisoconia. So do we have a difference of image size normally also in our eyes? Even in an emetropic eye, there is a physiological difference of retinal image size. And that physiological difference is around 5%. Got it? And this 5% of difference helps us in depth perception. It helps us in depth perception. But anything more than that is what we call anisoconia. How do you measure it? The name of instrument is by acinometer. Acinometer. And how do you treat it? What we do is the eye with a smaller image, we just put a magnifying glass to make it equal to the other eye. So the treatment becomes isoconic glasses. It is isoconic glasses. Okay? Okay. That was about your anisoconia, and these are the different refractive errors. We next talk about is your aphakia. So all of you, what is aphakia? We all know absence of lens. Now I want you all to think optically. What is the power in the lens? We have learned 16 to 17 diopters. Oh, we didn't revise that. But we very quickly, the power of the cornea is 43 to 45 diopters. Of the lens, it is 16 to 17 diopters. Index of cornea 1.37, you have learned with me. And for the lens, it is 1.39. It is maximum at the center of the lens, which is 1.4 or 1.41. Done? So you know that the major part of the refractive power is contributed by your cornea, and another next major is your lens. What is the total refractive power of your eye? You will say it is 60 diopters, 58 to 60. Okay. Now we talk about when you say aphakia. So aphakia means when there is no lens, 16 to 17 diopter is less in that eye. Less means hypermetropia. So what is aphakia? Can we also say it is a state of high hypermetropia? Aphakia is nothing but high hypermetropia. What will the patients complain? It will be the same, right? So difficulty in both far and near. He is not able to follow. It's a high hypermetropia. 16 to 17 diopters is less, right? So definitely his vision is not clear, and there are a lot of asthenopic symptoms, as we have learned in any hypermetropia. Now talking about that, when we examine this patient, What are the features that we see in an aphakic eye, right? So what do you see in this aphakic eye? We make a diagram to learn. So there is no lens, right? Anterior chamber becomes very deep. So we will write here, there is a deep anterior chamber, right? Okay. Nodal point, which was after bending by the lens rays, light rays were focusing behind. There is no lens and no bending by the lens. So nodal point recedes in front. So nodal point moves forward. Now, what is the normal position of the nodal point? It is almost 7.08 millimeter from anterior surface of cornea. This is normal in a normal eye. So that will shift in front. There was some question related to it, so I have mentioned this, keep this in mind. Then we have, of course, the support on the lens is lost, so you get an iridogenesis. We all know iridogenesis is tremulousness in the eye. And what is then the power? Of course, the power of the eye is now 44 diopters instead of 58 to 60 diopters. And no lens means no accommodation. Keep in mind, there is no accommodation. Right? So these are the features that we have to keep in mind for aphakia. And even the pupil, it is said to have a darker pupil and so on. Anyway, talking about treatment of aphakia. So when you say treatment of aphakia, primarily we can say there are three options to treat this high hypermetropia. Either we go for specs, contact lens or intraocular lens. What is the treatment of choice? We will answer intraocular lens. Then they have asked you what is the choice of IOL implantation, or choice of site of IOL implantation. Choice of site of IOL implantation, we will say it is posterior chamber or capsular bag. Posterior chamber or capsular bag. We have learned this in our lens chapter. We don't have to go into detail here. Right? Okay. So, and they have even asked you some pharma questions like this, that which is the strongest cycloplegic? We know it is atropine. We know, na? And secondly, they have asked you about which is the drug which is only, all cycloplegics are mydriatics, all mydriatics are cycloplegics except one mydriatic, which is not, has no cycloplegic action. And what is that? Do you know that? Yeah, phenylephrine, right? Anyways, so coming back to aphakia, now suppose we decide to treat it with specs. Now this is important, as in exam, all the things we are going to discuss under this. So when you are saying specs, what will be the power of the specs? That can reach from anything from plus 10 diopters to plus 14, depending. Now you can ask, okay, it is 16 to 17 diopters less, but you know, position of the specs is different and position of the lens is different. Therefore, this difference. Now, so this plus 10 to plus 14, such a high convex lens itself is a very big problem. So the questions they ask you is, what are the problems faced by the patient if the aphakia is treated by specs? So first of all, you have to be very clear, the problems are not due to aphakia, the problems are due to the thick convex lens. First thing, what can happen? So what does convex lens do? What did we learn? It magnifies. So, and you know, every diopter is magnifying so much, 2%, right? So magnification is very high. Okay? High magnification due to the high convex lens. Magnification is around 25 to 30%. Anything like that. Okay? Now, with a high magnification of this much percent, do you realize what will happen? You can tolerate. So, because of this, if this patient has aphakia in both eyes, no problem. But suppose there was a case of trauma and there is an aphakia in one eye. I cannot correct with specs. Why? One eye the patient is going to see so larger, 30%, 25% larger than the other eye. Isn't it? So, what will happen in that case? What will happen in that case? It is going to lead to a lot of difference in the image size. That means high IC and aniconia. And how much difference can I actually tolerate? Only 5%. And this is such a high difference. The two eyes cannot really be together now. So what happens? Double image, diplopia. Right? So note down that high magnification, and this high magnification की वजह से you said you have to write, we cannot correct a uniocular aphakia with specs. Right? Why? Because now this is going to lead to lot of difference in the two image size, high anisoconia, and this high anisoconia will lead to double image. Because these two images cannot fuse. They are too different. Maximum what I could have done, I could have tolerated 5%. Not more than that. Only that this much difference can be fused. So such a big difference, I cannot, the images don't fuse, and if they don't fuse, there is double image diplopia. That is point number 1. What is the next problem the patient can have? The next problem is, just understand, every lens has the aberrations, spherical, chromatic and prismatic. Let's have a look. We can write later. Let's understand. First of all, a very quick revision for you. What is the process happening? Refraction through a minus, that is concave lens. As you can see, the light rays, they diverge, and when you draw it behind, this becomes the focal point. You all have learned this. And when this is a convex lens, in a convex lens, the light rays are converging, so this is the focal point. This is a plus lens. In a minus lens, here is the apex and this is the base. Okay, so this is a concave lens. It's like two prisms above and below actually. So there, what you see, there is a divergence of rays, and this, when you meet it behind, the progressive behind this becomes a focal point. I hope you now remember, right? So this is the prism with the apex and the base. When you put it apex to apex, this is the minus lens, base to base, this is the base and this is the apex, then becomes the plus lens. If you remember some things like this. So this is the refraction happening through a prism. That was just a brief revision for you all. Now talking about aberrations. I told you all these lenses, there will be aberrations, right? So when you talk about aberrations, first is spherical aberration, which simply says that the bending of light ray from the periphery is always more than from the center. Okay, so these are the light rays, this is the optical axis, the red one, and the best focal point therefore comes here. So what is very important to understand, what is spherical aberration? Periphery say there is more bending than from the center, right? This is what is spherical aberration. Okay, then talking about next was, because of this bending and too much of bending of spherical aberration, patient is not able to see straight. Everything is a parabola for him, right? Everything is curved for him. For example, if you look here, this is what is called pin cushion effect, where normally this was the square which should have been looked like this, but it is looking like this due to the spherical aberration, and this is what is called as pin cushion effect. When it is due to the concave lens, it causes barrel effect. With a convex lens, this causes pin cushion. Concave, it causes barrel effect. All these are happening due to spherical aberration. Okay, we'll write this, just keep listening first. And second is your chromatic aberration, which means that the longer wavelength of the light is bending more, isn't it? So chromatic aberration is different color of the light is bending differently, right? Oh sorry, longer wavelength will bend little lesser and the shorter will bend little more. It is reverse. So we will write the second problem is, in a high convex lens there is high spherical aberration. And because of this high spherical aberration, nothing is seen straight. Everything is, even if the patient is looking at a tube light, it is more curved. So this is what is called pin cushion effect. You just saw what is pin cushion effect, right? Where this is the, though this is the normal, but this is how the patient looks due to the high spherical aberration. Then we talk about the third is your high prismatic effect. Okay, so what happens is that every glass, whatever we are using, at the periphery is a prism, right? So at the periphery, the prismatic effect is so much that nothing is seen clearly. That is why we have to match the optical center whenever you go for getting your glasses made. Optical center matching is so very important, because when you take out your glass and try to see from the side of the glass, it is not clear. Now what happens, I'm just simplifying, oversimplifying this for you all. Now what happens that when you are using a very high convex lens, right? So when you are using a high convex lens, this prismatic effect is so much that absolutely nothing is seen. So when you say nothing is seen, suppose this was the FAK glasses I'm using with strong convex lenses, and due to this effect, there's nothing is seen at the periphery. Because of the high prismatic effect, if nothing is seen, do you realize it is a scotoma? And because it is around my eyes all throughout, it's a ring scotoma. Okay? And when I am moving my head, my specs are moving along with me. So it is roving ring scotoma. Got it? So this is what you have to understand, how a high prismatic effect is leading to roving ring scotoma. Because of this is what is happening. The images are cut like this. And do you realize your visual field is unnecessarily being constricted? There is no problem in your optic nerve, but because of these specs, the visual field is constricted. So what happens if the visual field is constricted, and this is the FAK glass I'm using? You want to see two people sitting together. When I look at one, the other is, I can just see the periphery of the other, but he's out of sight. When I look at the second one, the first is out of sight. Now the second is out of sight. So this getting out of sight, due to this constricted visual field, I'm not able to see two people together here. This is what is called Jack-in-Box phenomenon. It's based on a toy. So this is the Jack-in-the-Box phenomenon. Okay, so we are going to write this. This roving ring scotoma will later lead to Jack-in-Box phenomenon. This is causing a constricted visual field, and this is going to lead to Jack-in-Box phenomenon. Right? So this is another problem of high convex. So what are the problems? High magnification, then high spherical aberrations can lead to pin cushion effects, and prismatic effects at the periphery particularly are causing roving ring scotoma and Jack-in-Box phenomenon. Right? I just wanted to simplify it as much as I could. I hope it was helpful. And of course, there are also chromatic aberrations. Right? So in any lens, when you're talking about, and it's a feature of every lens, all these aberrations, spherical, chromatic and prismatic. So there are some different ways of managing those effects, right? Like if I talk about spherical aberration, I can lessen it by using aspheric glasses, okay? Aplanatic surfaces, right? Spherical aberration, we can just counteract by using more of the aspheric, where the periphery is more flatter and center is more curved. That is why cornea is also aspheric, which decreases the amount of spherical aberration. Okay, if you want to note down, you can note down. So we cannot go too much into that detail. It's a time constraint. Also, we should be focused to what is asked. So next thing that we are going to understand and learn. Yeah, let's talk about this, that if this patient is a case of pediatric aphakia or whatever it is, even if the patient is your adult aphakic, but especially for pediatric aphakia. So do you realize here that once you have taken out, suppose you have done a cataract surgery in this patient. I think I've talked about this already. So you have removed the lens and you have put the intraocular lens. So in any patient, do you realize now there is no accommodation? If I talk about adults, in adults what happens? That if there is no accommodation, still he can see the far, so he can decide and use his near glasses whenever he is seeing the near. Right? Whenever he wants to, you can use near glasses. Now, or of course there are other methods like I talked about multifocal intraocular lenses and so on. Now, when you talk about a child will not know, I cannot decide, okay, now I am looking at the near, let me put it on. Now I am looking at the far, let me remove the glass, which is not possible. That is why we are writing that, especially in a pediatric age group, whenever you are giving a correction and you know that there is no accommodation, the patient has been aphakic or pseudo-phakic, we should always go for bifocals, right? So bifocals which has both distance and near correction. Please remember, near is added to the distance. You got it? Suppose a near correction of +1 and there is -3. So -3 + 1, something like this. Now this one is algebraic. So anyway, so always remember near is, and if it is suppose your far is +2 and another +1, so in the lower side it will become +3, something like this. So near is added to the distance. Either see, these are the three designs of a bifocal. Means in this glass, I can either put all throughout like this, divide the lens into near. This is called bifocal, executive bifocals. These are what are executive bifocals. But there could be other options, like I just put a near correction in this way, in this design, or in a round shape, and just impose the near correction there. Okay? But when he's a child, we should always use this. Why I am so much talking about the shape of the glasses? Because this was your exam question. So near, see, this was the specs shown to you in your exam, and they had asked you for about this, that it is a pediatric age group. We have to give this executive bifocals, where you're dividing in equally. This is the near part and this is the far part. Am I clear now? Yeah. So apart from that, of course, the other modalities we have discussed. Okay, so we just talked about how the treatment of aphakia when we are doing with the high convex glasses can, convex lens, glasses means specs here, is going to create so many problems, like what did we learn? High magnification, and second was spherical aberration, and third, of course, prismatic effect, which is causing roving. So prismatic effect, you are understanding? So if you go back to the how the refraction takes place or bending of light rays takes place across a prism, we have learned this, that the light deviates towards the base and the image towards the apex. So the same phenomenon is more at the periphery of the lens. We cannot go into too many details of the physics here. Just remember, because of this, the quality of vision at the periphery is affected, leading to roving ring scotoma, and that causes Jack-in-Box phenomenon. Okay, now comes a very important topic again for you all. Let's give the heading accommodation. When we talk about accommodation, everybody knows, we have discussed this so nicely in the lens chapter also. What are the 3 steps of accommodation? Very quickly for you all. It is first of all, there is a contraction of ciliary muscles, relaxation of zonules, which is causing more curvature of the lens, and more the curvature, more is the refractive power. Done? Okay. So whatever refractive power, increased power that you need for the near is taken care of by this process of accommodation. Rather, not only for the near, whether I am talking of near distance or intermediate. So either it is at 33 centimeters or it is at intermediate distance, or at, so both are taken care of by the ciliary muscles. Okay, and we know for far vision, the ciliary muscles have to be totally relaxed. Right? We learnt all this? Okay. So now what next you have to know? We have to be very clear about the concept of what do we mean by far point and what do we mean by near point. And few calculations around accommodation. So very simple, far point, which is also called punctum remotum. Okay. So what is punctum remotum here is farthest point where I can see clearly. Which is the farthest point where patient can see clearly. This is your far point. If you want to write, you can write it. And then what is a near point? Near point is, I'm making it absolutely very simple here. Near point also called punctum proximum. Okay, this is proximum. So when you talk about punctum proximum, we are talking about that the nearest point where the vision is most clear. That is your near point, right? So the accommodation is happening between these two. So what is if we take that distance to be, suppose remotum wala R here and P for the punctum, proximum, right? So what is the range of accommodation? This is one term you have to know. So the range of accommodation will be between these 2 points only, right? So range of accommodation is depicted as A, which will be equal to, which is far, R minus P. That is far point minus near point. Whatever distance, this is the range of accommodation. Then we talk about what is the par at far point? 0 almost, or it could be something depending on the refractive error. But if he is a emetropic patient, then the far point is an infinity, and infinity the par is 0. Anyway, so what is the one term was range of accommodation. Now we are talking about what is your amplitude of accommodation. You have to understand this well, okay, all of you, because some questions come from this topic. So amplitude of accommodation. Let us talk about what is amplitude. It means how much accommodation is exerted. That was the range. So that will depend upon par. Where is the par maximum? At the near point. So this time we depict it with capital A is equal to par at the near point minus par at the far point. Okay, so this becomes your amplitude. What did we learn? If we talk about the far point, keep in mind here, for an emetropic eye, these are important points, pay attention. For an emetropia, far point is infinity. And because it is infinity, the par will be 1 upon infinity, which is equal to 0. So, everybody remembers that? Par is inverse of focal length in meters. Don't forget that. All the calculations of that we are going to do will be working around these facts. Okay. So, if you want, you can note it down that this you have learnt earlier. A par is inverse of focal length in meters. Right? Okay, that was emetropia. Where is the far point of myope? For myopia, it is in front of the eye, note down. But when we talk about hypermetropia, we say it is behind the eye. Now this is again important, we will tell you why. Just note down, this is behind the eye. Right? So if the far point is considered behind the eye, actually why it is important? Because whatever value we read in a question, we put a minus there because it is behind the eye. Okay, so you all know this now, that how the hypermetropic eye will focus the light rays behind the retina, right? So just this will help you to understand and learn that the far point is generally considered behind the eye. Okay, once we know this, now let us solve a few questions here. So these are the questions they have asked you in your exams this way. So this has already been asked. So we'll solve this. With a near point of 20 centimeters, a hypermetrope of +4 has to exercise accommodation of. So what are they asking you? They are asking you the amplitude of accommodation for a hypermetrope of +4, where his near point is already given. So what was amplitude? Amplitude was par at the near point minus par at the far point. Correct? Now they are asking you this amplitude of accommodation. Now what is the par at near point? Near point is 20 centimeter. So 1 upon 20, it has to be meters, so it becomes 100 upon 20. Correct? So this is the par, that is 100 upon 20. Okay? So the 5 diopters will be the par at the near point, with this is P is equal to 5 diopters. Come to the par at the far point. It's already given here that it is +4 of hypermetropia. So R की value हो गई 4. But what is important, because this patient is a hypermetrope, we always take it as negative because the far point of a hypermetrope is behind the eye. So we are going to put it as -4. Right? So again, don't go too much into detail of the physics. I have just told you how to remember that why it is behind the eye. This much is enough. So this is -4. So when you say it is -4, what will be the value of A? It is 5 minus -4. Correct? So this much we all know, this equals to 9 diopters. So our answer will be 9 diopters. Hope this helps. We come to the next. Next question has not been asked but may be asked anytime. Let's solve this also. You will enjoy solving it. What is the near point of it? It is based on the same formula. So what is the near point? They are asking you the near point of an emetrope person. with an amplitude of accommodation as 7 diopters. So here when you say A is equal to P minus R, A is already given as 7. So 7 diopters the amplitude. What is the power at the near point? We do not know. But what about the power at the far point? Power at the far point, E metropia, it has to be far point at infinity, so the power is 0. That means what is the value of this P? We can write it P, why to confuse? This is P. So P will be it becomes, what will be the value of the P? Again that is equal to 7. Right? So if the value of P is 7, what is the near point? They are not asking you the power at the near point, they are asking you the near point. So near point will become, what is it? Inverse of focal length in meters, na? This is what it is. So here it will be your 100. So inverse of focal length in meters, power is equal to, so this becomes 100 upon 7. Right? That is equal to 14.2 centimeters. Right? So this is the way we are going to solve, because power is equal to inverse of focal length in meters. This is what it is. So this is what you will do in meters, right? So this is how we will solve our questions. Right, all of you? So another thing is, how are you going? What is this instrument, all of you? So this is what is your RAF ruler. RAF here stands for Royal Air Force. Okay. So RAF ruler is mainly helpful for us to assess the near point of convergence and the near point of what is the accommodation, where the accommodation is happening. Okay. So you keep, this is where the patient is fixing the whole instrument on the nose, and this is moved closer and closer. Wherever the point where, so the letters are written on the box. Whenever there is a diplopia, that becomes the point or the near point of convergence. Okay. So near point of convergence is where the patient has diplopia, and near point of, you can still move further, and the near point of accommodation will be when this patient has got blurring of vision. Okay. So total blurring, then this is the near point for accommodation. That was about your, how do you measure the near point of convergence and accommodation. We next talk about a few questions that we should know. You all know this, that error of accommodation is what is called presbyopia, right? So, and how do you treat it? Common sense, it just means less power for the near, so we are giving convex lenses, but this is only for near. So this is the place where the question of only near comes, okay, not an hypermetropia. So if you realize a patient of myopia, hypermetropia, you have to wear the specs all the time. But when you talk about presbyopia, you are going to wear it only when we are looking at the near, okay. So then only we use the presbyopic glasses. Few questions, I think I have mentioned it earlier also, but this needs some mention here as well. If you talk about presbyopia, so the first question is, what is the average age when it will happen? So it is around 40 years, plus minus here and there, little bit variation is there, but around 40 years. So the question is, this we learn for an emetropic person, okay. Now, if your patient is already a hypermetropic, will it occur before 40 or after 40? If your patient is myopic, will it occur before or after 40? So this is your exam question. Think yourself. Hypermetropia is already a situation of less power. This is also a situation of less power for the near. Therefore, whenever your patient is hypermetropic, we are going to learn in hypermetropia, it is less than 40 years, and in myopia, you will say it is, the presbyopia sets in after 40 years. Okay. So the patient's presbyopia sets in after 40 years, and here it is before 40 years. This was one question. Then secondly, they have asked you, when you are giving the correction for this presbyopia, sometimes we can roughly give it according to the age. So this also is your exam question, and we should all know, if we start giving a presbyopic, so at around an age of 40 years when you start giving, it may be little less, but generally we learn it as +1 diopter spherical. Okay, at 45, we can make it 1.5 diopter spherical. I'm simplifying it. You can find some variation in the books. Just follow this one. For 50 years, now this is 2 diopters. then 55 years, now this is 2.25 diopters, and for 60 it becomes 2.5 diopters. Right? So this is the rough assessment about how much diopter a person will need if he is a emetropic person according to the age of the person. Right? So many people, they expect that, okay, you're wearing glass, why it is increasing, why the number is getting more. But this is a normal phenomenon. I keep explaining to the patients, just like graying of hairs, this is going to happen. Right? So this is another thing they asked you. Third thing is about what are the causes of frequent change of presbyopic glasses. When we talk about frequent change of glasses or frequent change of presbyopic glasses, we have to keep a few things in mind, how we are going to learn it. Three main points. First, it could be your intumescent cataract, where the swelling is differing at time to time, and because the swelling is different, curvature is different, therefore frequent change. So we call it intumescent. Mainly we are talking about early cataract. That is intumescent cataract. Second is we will learn late glaucoma, that is late stage of primary open angle glaucoma. Now this is more factual. There's no much explanation here for this one. And third is your diabetes. See, this is a very, very common mistake we all do. When it is asked, we answer, okay, what is the cause of frequent change of presbyopic glasses? Options are diabetic cataract, this cataract, that, and then intumescent cataract. So we all tend to mark diabetic cataract. Please understand, it is not diabetic cataract. It is the diabetes itself which is causing the frequent change of presbyopic glasses. Got it? Cataract puchega, then you have to answer intumescent cataract. So why diabetes? When the patient is hyperglycemic, there is more swelling of the lens, there is more shift towards more power because curvature is more. So we learn like this. So how do we learn? That in hyperglycemia, we get a myopic shift. It is the shift. Okay, whenever you read this myopic shift, it doesn't mean he has become myopic. Shift means from +5, even lessening to +4 is a myopic shift. Or going from -5 to -6 is a myopic shift. So this way. So hyperglycemia, it can cause myopic, and vice versa. In hypoglycemic condition, the patient will have hypermetropic shift. Okay. So do you realize something here? It's very important when I'm doing a refraction in a diabetic patient, the blood sugar should be normal or around normal. Okay. If there is variation in the blood sugar, this patient is again going to come to me for the refraction. He is not going to be happy with me. Right? So keep this in mind. So these are some important questions in and around accommodation and presbyopia. I hope you understood it. Right? Next we talk about a most interesting part. I said most interesting because many of you find it very difficult also, but it is not. We talk about retinoscopy. So in our introduction also we just discussed this, that please, retinoscopy is a misnomer. It's not an instrument to see the retina. It is an instrument for assessing the refraction of your eye. So retinoscopy, we will first write, as an objective method of refraction. Why do you need this objective method of refraction? So suppose we have to assess a refractive status of a small child, okay, or a person who cannot respond properly. Then what will you do? Right? You understand objective means what? That the patient is not participating. I'm just trying to assess the number in your eye. So when you are participating, suppose I ask you, I'm doing your refraction, I ask you, okay, which lens is clearer? Ye wala theek hai ki ye wala? This one or this one? So you are the boss. You are telling me, okay, this is clearer, this is not. This is a subjective method. But if I'm not asking you and I'm assessing your refraction, this is what is objective method of refraction. Got it? Okay. How do we do it? Let's try to understand. So generally the distance between examiner and the patient is either 1 meter most commonly, that is what they're going to ask you, or it can be 2/3 of a meter, 1 arm's distance. Anyway, so what do we do? Suppose I'm going to show you a video also, so don't panic, just listen. This way you understand better. So this is your retinoscope. Now the light, so what is a retinoscope? I told you, for objective method. So these days a self-illuminating streak retinoscope which throws a line of light on the pupil is mainly used. Or we will just have a look at the other types. But let's first understand retinoscopy. So what I do here, I'm sitting at 1 meter distance, right? So behind the patient is either the light bulb when I'm using a plane mirror retinoscope, or let me not confuse you, this is self-illuminating, the light is coming from here and going in the patient's eye. Chalo, आगे बढ़ते हैं. So if this is the retinoscope and the line of light is falling on the patient's pupil, right? So if this is the instrument and this is the line of light on the patient's pupil, what is my first step? I move my instrument and see whether this reflex is moving along or not, or is it moving opposite. If it moves along, this is what is called with the movement. If it is moving opposite, this is what is called against the movement. Now this I am going to check in both principal axes, 180 also. Now I turn it like this. I am going to check it is with the movement or is it against the movement. Whatever finding I get. So whatever, so you can just see, let us make this for ourselves that this was suppose the pupil. What do we see here? That we see a line of light here. This is the light reflex I am seeing, and I am trying to assess whether it is with the movement or against the movement. Now, in front of me is the refraction box where there are a lot of lenses. I pick up a lens according to what movement I got. Was it against or with? I pick the lens, put in front of the patient's eye, again assess. Suppose I started with +2. So I am putting in front of your eye +2, I am assessing what is the movement now, with or against. Okay, suppose it was, okay, if it was with the movement, let's see like this. For example, the first movement that you saw was with the movement. If it was with the movement, I use a plus lens. So I started with suppose +2. Moved it like this. No, it is still moving. Okay. +3, again assess. +4, again assess. Till a time where when I put the lens, there is no movement in the patient's reflex. I don't see any line of light. Everything is just illuminated. And this is what is called point of neutralization. And this is what is called point of neutralization. And the lens by which I got this point of neutralization is my retinoscopic reading. So, suppose I write here as an example, +4, +6. This simply means that I could get this point of neutralization at 90 degree with +4. At 180, I could get it with +6. Was it all of you? So, once I got this point of neutralization, and this is not the exact number in the patient's eye. Why? So, I would have actually done it at some distance. So, and second thing, I may have put some mydriatic or cycloplegic in the patient's eye. So, this is my retinoscopic reading. Comes the second step where I am going to subtract my correction factor. So, subtract the correction factors. Okay. So, correction factors are, if you talk about the correction factor, I said it can be distance factor or it is cycloplegic factor or both, right? Suppose I have used a drug, then it is both. For distance, two options we have to remember, 1 meter or 2/3 of a meter. We already know it is inverse of focal length in meters. So, here it becomes 1 and this has to be subtracted, and here it becomes 1.5 which has to be subtracted. This much power, right? Because of the distance. Coming to cycloplegic, if it is atropine, let us say it is 1 that has to be subtracted, strongest cycloplegic, or it could be any other cycloplegic, let us learn as 0.5. Right? Somewhere it is written for cyclopentolate 0.75. Let's not confuse ourselves. We are using it little lesser. So just learn this much, make life simple. Now, suppose in this example, I tell you, I did this retinoscopy at 2/3 of a meter with Tropica Cell Plus. What do you think was my correction factor? It was 2. 1.5 and point is 2. So, I am going to subtract that from my retinoscopic reading, means I will subtract my correction factor. And what is my corrected reading now? It is +2 and +4. So, this is the corrected reading, and it is this corrected reading after subtracting all correction factor which is the actual number in the patient's eye. What next we have to learn? What is the next step? How to give a spectacle prescription. Right, all of you? Chalo, let's go back to the step 1 where I was just assessing whether it is with the movement and against the movement. I think all of us have learnt this in our MBBS also, that if you are getting a reflex of with the movement, then this is either patient is emetropic, hypermetropic, or myopia of less than 1. If you are getting against the movement, this is myopia more than 1. And if no movement, it's already a point of neutralization. It is myopia equal to 1 if I am doing, from where this 1 came, if I am doing at 1 meter distance. Right? So this inference we all know and we have learnt it very well. So today we are going to understand why we are learning this inference. We will understand why we are learning this. So do you want a quick revision what we learnt? We have to first do this retinoscopy, try to find out with which lens. So suppose instead of with the movement, I had in this patient against the movement, I would have picked up a minus lens, okay? And similarly, I would have just tried to find out the point of neutralization with a minus, and whatever lens I could get that point of neutralization is my retinoscopic reading. Subtract the correction factor, get a corrected reading. This is the actual number. Simple? Okay, now what is point of neutralization? What do we mean by with the movement, against the movement? Confusion? So let's see and watch this video first. After that, we are going to learn the third step, and that is your spectacle prescription. Okay, so when you watch this video, this is a retinoscope and the light that is falling on the patient's pupil, and this is the examiner who is seeing this light in this way, right? Okay, so what is the basic of with the movement, against the movement? Let's first understand. If there is a nice focusing on the retina, what happens when you move your instrument, the source of light, the instrument that I was moving, this point, the arrow that is showing, it is not moving, right? That point is still. This is what is point of neutralization. Now suppose my patient is a hypermetro. Where will be the focusing now? It is behind the retina. Now when I'm moving my instrument, what are you getting on the retina? We get with the movement. Look at the arrow. We are getting with the movement in this case. And if we just put and neutralize this with a convex lens slowly, so this much is not enough, we change the convex lens to a stronger strength, and finally what happens is that this is now getting focused on the retina. Once this happens, this is the point of neutralization. That means with this lens, I can focus on that. So that is what is my retinoscopic reading. Got it? And if it is a case of myopia, means what happens? The focusing is in front of the retina. So if the focusing here is in front, can you see it is against the movement? In the direction wherever my instrument is moving, this is moving against it. Okay? So this is the basis and why you are learning this inference. Now we talk about the next important thing is what is with the movement and against the movement and how we are doing the retinoscopy. So you just saw the streak retinoscope. The line of light is falling on the patient's pupil. So suppose this is the patient. See, this is the reflex that you see in the patient's pupil, and this is what do you call it? With the movement. Right? Clear? In both the axes. This doesn't seem to be exact 180, but in both the axes at 90 and 180, we are going to this one is 90. So we will be assessing it. After I know with the movement, I am trying to neutralize with the plus. See, I try to do this. Oh, it is still with the movement. Right? Now I increase the strength further. For +2, it is still moving as with the movement. Right? And with +3, now watch all of you, this is what is point of neutralization, where in spite of moving my instrument, there is no movement of reflex. This is what is called point of neutralization. If I'm overcorrecting, I'm making the patient myopic. See what is happening. This is what is against the movement. Right?